मैं क्लास के बाद समझाती हूँ. All right. Good morning, everyone. We are doing chemical bonding as a part of our chemistry course this time, and we know that we've already dealt with so many things now in chemistry. All right. We are doing chemical bonding as of now. We've already had 3 lectures on it, right? And in chemical bonding, what we start up with? We started with discussion of chemical bonds, followed by your VSEPR theory, followed by your VBT, followed by your molecular orbital theory. All right. Now, one very important thing that I want you to pay attention to is, like last time I was telling you a story, if you remember, for VBT and MOT. Let's go back to our last topic in the sense periodic properties, in which I did quantum model of an atom, where I did talk about the Schrodinger wave equation. You remember that? Now to form the base, you've already done VBT in details. What was your Schrodinger wave equation? H operator psi is equal to E psi. Now here I would like to tell you, because there are questions in the examinations which have been asked. This is your energy operator. What is your energy operator? It is a combination of kinetic energy operator plus the potential energy operator into psi is equal to E psi, because energy means what? It is kinetic energy plus the potential energy. Alright, and please remember that the kinetic energy has an operator. If you can just go through it once, no need to remember. That is minus h square upon 8 pi square m del square by del x square. Have you done differentiation? This is like kind of d square by dx square. In books you will find it written as d square by dx square. So this is only your kinetic energy operator. Alright. Now your potential energy operator will be something that will be either, if it is a simple harmonic oscillator, you know that the potential energy is half kx square. ठीक है? That multiplied by psi is equal to E psi. I repeat it again. When we did the quantum model of an atom, in that I did tell you that it was based on the concept of quantization. Now you all very well remember that what is the difference between quantum levels and a continuous level. When you talk about quantum level, you are talking about microscopic entities. When you are talking about continuous level, you are talking about macroscopic entities. When you are talking about microscopic, you know that each microscopic particle is represented by a wave function, right? Now this wave function, and you can solve for this wave function using the Schrodinger wave equation. Now in Schrodinger wave equation, what you have is your H operator is equal to kinetic energy operator plus potential energy operator. I am telling you that in quantum mechanics, each of the operator has some expression associated with it. Like for kinetic energy, it is minus h square upon 8 pi square m d square by dx square. Repeat it once with me. Minus h square upon 8 pi square m d square by dx square. What is this? Kinetic energy operator. Now V is your potential energy operator. When you open it up, you will find Schrodinger wave equation given in so many forms in the examinations. So that is why I have taken it up, because now from here I will tell you what is the basis for your valence bond theory and your molecular orbital theory. Okay, I repeat it again. What is your kinetic energy operator? Now all of you all tell me. Minus h square upon 8 pi square m del square. Alright, okay, and then let me just tell you, this you will be doing in maths and physics also. When you have this in all the 3 dimensions, it's represented by this del square. Okay, that is nothing but del square by del x square plus del square by del y square plus del square by del z square. That is your complete del square. These are partial differentials. And you know that already it is associated with Heisenberg's uncertainty principle. So nothing is certain in quantum mechanics. There is always a probability associated with it, that it may be present here, there or somewhere else. There is always a probability factor. Whenever you have something which is exactly known, you use an exact differential, which is d square by dx square or d by dx. Alright, whenever you have some kind of an inexact differential, that means there is a probability associated with it. And you know, when you talk about a microscopic entity, there is always a probability associated with it. So this, whenever you convert this D into some kind of, this is called dou also, this is called del also at times. So then in that case, these are the partial differentials. So these are used in quantum mechanics because there is nothing that is certain when you are talking about microscopic entities. This was your Schrodinger wave equation, which you know that it can be solved. It can be solved only for single electronic systems. It can be solved only for single electronic systems. This is what we had seen. Now, what will happen if I talk about multiple electrons? Let's take up a simple example. That means it can be solved for hydrogen atom. That means it can be solved for hydrogen atoms and similar systems. It can be solved for hydrogen atom and similar systems. Now, if I talk about a molecule of H2, can it be solved using Schrodinger wave equation? No. Why? Because now you have 2 electrons, right? And let me just talk about the hydrogen molecule and let's see how we can actually solve for it. See, in this case of hydrogen, that means this is made up of 2 hydrogen atoms, HA and HB, and each of them has 1 electron. So let there be 1 electron here and let there be second electron here. Okay. Now I know that I can solve individually for each of these electrons because I can solve for this hydrogen atom, I can solve for this hydrogen atom, right? I can do that. If I consider 2 of the atoms to be independent of each other, then in that case I can solve for the wave function of this and solve for the wave function of this. Is that clear? Right? In reality it's not correct because you are talking about only hydrogen atom. But what do we want it for? We want it for the hydrogen molecule. So for this there are 2 approaches. One is what you have already done, that's the valence bond treatment. That is based on complete hybridization. But the basis comes from quantum mechanics only. And just understand that in valence bond treatment, this is a very important statement asked many a time in the examinations. We consider each electron to be associated only with its own atom. जैसे hydrogen molecule है, in that you will consider the first electron to be associated only with atom A and the second electron to be associated only with atom B, and the 2 atoms will be independent of each other. Independent means there is a bond otherwise, but then this is an independent atom and this is an independent atom, and then they are clubbed together to form hydrogen molecule. This is an assumption. We are just assuming that both the hydrogen atoms are independent of one another. Then we will solve for one hydrogen atom once and we will solve for the other hydrogen atom once. Because Schrodinger wave equation can be solved for hydrogen atom. तो एक एक करके solve करके then we will club. So in that case, whenever we talk about the wave function, then in that case remember that the wave functions are multiplied. And as I told you, each microscopic entity is represented by a wave function. So here in this case, each hydrogen atom will be represented by a wave function. And I am saying according to valence bond treatment, what you have is both the atoms are independent, that means their wave functions will be multiplied. And I am saying the first electron is associated only with A and the second electron is associated only with B. So this will be your valence bond wave function for hydrogen molecule. And you can put it as HA and HB because this is hydrogen atom A and hydrogen atom B. You can put it like this also, HA and HB. Is that clear to everyone? Because when you are doing valence bond treatment, what is your approach? Like for example, if you are solving for any molecule, say let me just talk about, okay, let's take up the simple example that you've already done. In this, what do? First of all, you write down the ground state configuration, which is NS2, NP5 and ND0. This is it. Then you excite it. When you excite it, it becomes NS2, NP5 this should be plus 7. So in this case you would be making 2 jump from here and 1 jump from here, right? Is that clear to everyone? 2 plus 3. Do you want me to show it? Otherwise we'll get it out. Yes. We are talking about it. Just see. First you see this. I am coming to that point. See. Now this is your NS and this is your NP. This is clear to everyone? NS2 and you have NP5. What was the next thing you used to do? In the long method you used to find out the oxidation state. The oxidation state of I is plus 7. So in the excited state, now I'll just shift it. In the excited state you will have like this. Right? And then you have each of the F's forming a bond with the sp3d3 hybridized atom. So what it does, it forms the hybridized atoms placed on the central atom first, and then these combine with the other atoms with the neighboring atoms. Alright? Like for example in this, so what happens is like you considering all the electrons to be centered on one atom first, and then they all together combine with the other atoms. You're getting the point? So that is what I'm actually stating in valence bond treatment. What happens is in this each electron is associated only with its own atom, and here again each electron is associated only with its own atom. One is associated only with A and 2 is associated only with B. Now the point, a question has been put up, then it is not talking about the covalent character which we talk about generally in valence bond treatment. Now here when you have to talk about one being associated with A and 2 being associated with B, this is understood to everyone? ठीक है, अब एक स्टेप आगे और चलते हैं कि ये तो माइक्रोस्कोपिक एंटिटी है, तो it is also a possibility that the two electrons get exchanged. Bond तो बन गया. Then there is again a possibility that the two electrons can get exchanged. So then in that case this 2 can come here and this 1 can come here because electrons are microscopic entities. So what is happening is like there is a mutual exchange of electrons, and then what happens is you can add another possibility that according to valence bond treatment now 2 is associated only with A and 1 is associated only with B. But you have to remember this much, that when each electron is associated with its own atom, it is your valence bond treatment. Is that thing clear to everyone? That is your valence bond treatment. Yes. Now second actually valence bond treatment initially was, when it was given like this. But then this could not give you correct results. So this was a modification which was brought about by Hitler in London. And you must have done these names only for your valence bond treatment, Hitler and London approach. Hitler and London, they actually brought about this modification stating that because electrons are a microscopic entity, they cannot just remain stationary. So there will be a mutual exchange of electrons, and you have to remember that the valence bond and treatment will give you the wave functions in such a fashion where each electron is associated only with its own atom. Okay? And we take each of the atoms to be independent of one another and we multiply them to get the total. Yes? While solving the wave equation, no, we consider the total part. But in the exam, just in case, this question will be asked, if at all, only in your entrance examinations. That is only to check whether you know or not that each electron is associated only with its own atom. So even if this is given, this you will take as the valence bond wave function, and even if both are given, then also it will be the valence bond wave function. And now that you have done valence bond treatment in detail, it was like logical to talk about it now. And we are now going to start out with the molecular orbital treatment. Now one kind of wave function is like this, and let me tell you, these are known as the trial wave functions. Trial wave function matlab, if we are solving for a multi-electronic systems, we as it is do not know what is the wave function and what is the energy, right? So now if I have to actually Say if I have to make you ask the weight of the notebook that you are carrying, alright, you will make arbitrary guesses. You will make arbitrary guesses, it may be 500 grams, it may be 1 kg, or depending upon what notebook you are carrying. But if I give you a reference to it, I tell you that this is the notebook, check it, this weighs 1 kg. So uske relation mein you can always find out. So let me tell you, whenever you are finding out your valence bond wave function, it is some kind of a trial wave function. It cannot be exact. Is that thing clear? So the energy that you get is also not going to be exact, it will be kind of an average or an expectation value, that this is what you expect it to be. Now if I tell you that this notebook carries 1 kg weight, you will check that and check yours. If it is lighter, you will say it is less than that. If it is heavier, you will say it is more than that. Right? So it is that kind of a relation where you know. Now you know that wave function of a hydrogen atom A can be solved. Wave function of hydrogen atom B can also be solved. Right? And because they can be solved independently, you can multiply them and get the trial wave function according to valence bond treatment. Clear with this? Can I move on to the molecular orbital treatment now? Now what is the difference in the molecular orbital treatment? Both of them talk about the combination of atomic orbitals only. Now here, one thing that I stated initially while talking about quantum model was that each electron is associated with a wave function. Similarly, each atomic orbital is also associated with a wave function. Just as psi A was an atomic orbital because you were talking about hydrogen atom A. Now, talking again about hydrogen molecule only so that you understand well. In valence bond, what was happening? 1 was associated only with atom A and 2 was associated only with atom B. What are these? These are the electrons that I have numbered. Okay. Now in molecular orbital theory, what happens is each electron is associated with all the nuclei in your molecule. Because this one has an electronic cloud, molecular orbital treatment is again another kind of a trial wave function which suggests that each electron is distributed over the entire molecule. That means that if I am writing down the wave function of electron number 1, if I am writing down the wave function now according to the molecular orbital method, then my 1 is associated with A also and 1 is associated with B also. Do you get it? Now in molecular orbital approach, what you have is each electron is interacting with all the nuclei of the system. Valence bond mein kya tha? 1 is associated interacting only with A. It is not bothered about B at all. And 2 was interacting only with B. Right? Each electron with its own atom. Now here in case of molecular orbital approach, each electron is simultaneously associated with all the nuclei in your system. So that means agar first electron की बात कर रहे हो तो it is interacting with A and B simultaneously. अगर second electron की बात कर रहे हो तो it is interacting with A and B simultaneously. So another for this will be the second, for the second electron also now it will be 2 being associated with A, you tell me, plus 2 being associated with B. So this is for the first electron and this is for the second electron. Now this is the basis that you just have to understand for the molecular orbital theory. The molecular orbital theory, it was developed by Mulliken and Hund. What we are doing is like the molecular orbital theory, it was developed by Hund and Mulliken, and it is primarily talking about the entire molecule as a unit with all the electrons moving under the influence of all the nuclei present in the molecule. That means each and every electron is associated and moving under the influence of all the nuclei. When you are talking about the nuclei, you are primarily talking about the atoms. ठीक है? इसका I repeat it again. What was the difference in case of valence bond theory? In case of valence bond theory, when we talked about hydrogen molecule, I stated that in that case the total wave function will be in which one electron is associated only with A and the second electron is being associated only with B. So each electron with its own atom. Whereas in case of molecular orbital treatment, what you have is, if you are talking about wave function of the first electron, then in that case the wave function of the first electron is associated both with A and B simultaneously. And if you are talking about the second electron, then the second electron is associated with A and B simultaneously, and the total for H2 molecule according to molecular orbital will be, the two electrons are independent of one another. So what you will have is, you will have psi of 1 into psi of 2. This will be your total molecular orbital wave function according to molecular orbital theory, and this will be your valence bond wave function according to the valence bond theory. So please remember that in molecular orbital theory, the electron moves under the influence of all the nuclei and is interacting simultaneously with all the atoms in the system.
That means the valence bond theory contradicts to
You won't say it contradicts, because यहाँ पे भी what you are doing is, you are talking about an atom individually. So this is also a trial wave function and this is also the trial wave function. Both of them will give you different results which will be comparable. Same होंगे but exactly exact same value नहीं आएगी, because approach different है. Now you hold your nose like this or you hold it from the other way. It is just that you should be able to hold it. That's the point. Clear with this? Now you can just note down these salient features of molecular orbital theory. Remember that, like an atomic orbital, how is a molecular orbital formed? First you tell me. It is formed by the combination of atomic orbitals. When two atoms combine, what is formed? A molecule is formed. So similarly, whenever atomic orbitals combine, what is formed? Molecular orbitals. So like an atomic orbital which is around the nucleus, there are molecular orbitals which are around the nuclei of a molecule. Atomic orbitals surround your atoms. Similarly, molecular orbitals surround your molecule. Molecular orbitals possess different energy levels. Like atomic orbitals also possess different energy level. You have 1s, then you have 2s, then you have 2p, 3s, 3p, 4s, 3d and so on. Similarly, molecular orbitals also have a particular energy level that is followed. Then the next thing is that the shape of the molecular orbitals are dependent on the shape of the atomic orbitals. Now the shape of the molecular orbitals is dependent upon the shape of the atomic orbitals. Means what? Just understand, atomic orbitals क्या होते हैं हमारे पास? S, P, D, F, ये सब क्या हैं? Atomic orbitals. Now if I am talking about the combination of an S with an S, एक चीज याद रखना, whenever you have two atomic orbitals combining with one another, there are two possibilities. One, there will be a positive combination, and second there will be a negative combination. दो ही possibilities हैं, या तो add होंगे या subtract होंगे. तो इस केस में जब मैं s orbital को s से combine कर रही हूँ and there is a direct overlap along the internuclear axis, then what kind of a bond will be formed? Sigma bond. Whenever there is a direct overlap, it will always be sigma bond. कुछ points याद रखना. Whenever you are talking about the direct overlap of the internuclear axis of the atomic orbitals along the internuclear axis, it is a sigma bond which is formed. Whenever there is an indirect or a sideways overlap, then it is a pi bond. Okay. Now, when you talk about the atomic orbitals, look up here. Then remember that there is a sign convention that I am putting. ताकि जब मैं ऐड करूं और सब्ट्रैक्ट करूं, you will be able to understand the difference. S orbital is spherically symmetrical. I am putting a plus sign. Normally for P orbital, P is a dumbbell shaped, right? Remember that I will always take the positive sign in the increasing direction of the axis. अब increasing हम किसको मानते हैं? For x it may be this, for y it may be this, and for z this may be this. So whatever you have, the increasing direction will have a positive sign and the decreasing direction will have a negative sign. Is that clear? Positive, negative. Now another thing, whenever you have a positive interacting with a positive, then always you will say that the combination is in phase. whenever you have a positive interacting with a positive, you will say the combination is in phase, और जो आपको मिल रहा है वो एक bonding molecular orbital है. What you are going to get is a bonding molecular orbital. ठीक है? And whenever you have a positive interacting with a negative, say any orbital, positive interacting with a negative, you will say that the combination is out of phase and the resultant will be an anti-bonding molecular orbital. Okay? Now some important things to remember. I am telling you sign convention. साइन हम क्यों डालते हैं? ताकि जब प्लस माइनस करें तो हमें कुछ कुछ समझ में आए कि व्हाट इज हैपनिंग एंड हाउ इज जनरली द कन्वेंशन. यू कैन टेक इट टू बी द अदर वे अराउंड आल्सो, बट फॉलो इट थ्रू आउट. But by convention, the positive sign is always taken in the increasing direction of the axis. And for S, because it is spherically symmetrical, we are taking generally a positive sign. Okay. Then the other thing that I am telling you is like a direct overlap will result in a sigma bond. An indirect overlap will result in a pi bond. That is also clear. Now, if same signs are interacting, bonding molecular orbital, and if opposite signs are interacting, then anti-bonding molecular orbitals is what you have to understand. Clear with that? Now here, let's talk about what are the two combinations which are positive possible. One is a positive linear combination, the other is a negative. या तो वो दोनों ऑर्बिटल्स ऐड होंगे या फिर सब्ट्रैक्ट होंगे. ठीक है? ऑल दीज पॉइंट्स आर क्लियर. नाउ यू विल टेल मी व्हाट काइंड ऑफ अ बॉन्ड विल बी फॉर्म्ड. An s orbital interacting with an s orbital. So here you have the positive signs interacting. So this will result in a bonding molecular orbital. Alright. And s is located right in the center. It's spherically symmetrical. So it is about the internuclear axis. So what will you get? You will get a sigma. So that means you will get a sigma bonding molecular orbital. And the resultant shape, this is what I stated. In molecular orbital theory, the resultant shape is just dependent upon what? The resultant shape is dependent upon the shape of the combining atomic orbitals. Clear with that? Right? Now I told you that there are two kinds of combinations which are positive. Once it will get added, the other time it will get now subtracted. Now if I subtract a plus minus of plus, so then in that case what will this sign become? It will become minus. ठीक है? ये भी S है, ये भी S है. बात समझ में आई? You have a positive combination that is resulting in sigma bonding. Then you have a negative linear combination that is like a S minus of S. Basically how is it written? इसको हम ऐसे भी लिख सकते हैं, psi of 1s plus psi of 1s. बात समझ आई? This is nothing but this is psi of 1s plus psi of 1s of atom A, and this may be atom B. Alright, and similarly you will have here psi of maybe 1s of A minus psi of 1s of atom B. मतलब atoms दोनों different हैं, दोनों के s orbitals combine कर रहे हैं. अब ये plus और minus पहले तो internuclear axis के about ही हैं. So this will be, the resultant will be sigma. But opposite signs are interacting, so this will be out of phase or anti-bonding. So this anti-bonding is represented by a star. Bonding is generally represented just like this. Sigma, if it is written like that, it's sigma bonding orbital. And if it is anti-bonding, it will be represented by a star. So you have a sigma of 1s and you have a sigma star of 1s. So basically for 2s also similar, 3s also similar, because all of them will have combining s orbitals. ये चीज समझ में आई है? ठीक है? Do you want me to repeat it again? It is about the internuclear axis. So that is why it will be sigma bond only. And when same signs are combining, we get a bonding orbital. And when the opposite signs are combining, we are getting an anti-bonding orbital. Now, yes?
Same signs are both negative.
Then also bonding. If अगर मान लो आपको नई पॉजिटिव साइन पसंद, तो आप इसको भी नेगेटिव मान लो, तो नेगेटिव प्लस नेगेटिव क्या होगा? It will be a negative. So then it will be a sigma bonding only. And अगर आप वैसे by convention आप प्लस प्लस लेके चलते हो, but now if you have a doubt, then negative minus of negative will be your plus. So again it will be like an anti-bonding orbital, which will be like this. Now we had put it as plus and a minus, so it will be plus and a minus. और इसमें क्या है ये क्या है हमारा node and then you will get a nodal plane about the node. ठीक है? So understood the shape of the molecular orbital. Now you will tell me, I will not tell you. Look up onto the board. S is done. और सब समझ में भी आ गया है. मैंने बोला है whenever we have the combination of two atomic orbitals, there will be a positive and a negative combination. Second thing, I told you if the same signs are overlapping, तो bonding. If opposite signs are interacting, तो anti-bonding. If it is about the internuclear axis, तो sigma. If it is sideways overlapping, then pi. So now, let me talk about x. Let z be the internuclear axis. ठीक है? तो px will be like this, and py will be px of 1. Say 2px मान लो. So then in that case, if I am talking about psi of 2px plus psi of 2px, then it will be what? Plus minus. ठीक है? Plus of plus minus. Let this be my x-axis. So now tell me, what will be the bond formed? It will be a sigma or a pi? Pi bond. What will happen? Are the same signs going to interact? The positive will interact with positive. So that means it will be pi bonding. So I'll just let it remain like that. So in this case, I will get a resultant plus and a minus. Right? So this will be your pi. And let me tell you, if z is the internuclear axis, तो y में भी sideways overlap ही होगा. Y में भी. So this can be either px or this can be for py also. अगर px ऐसा है and z is the internuclear axis, then py also will behave the same because x is mutually perpendicular to z axis and y is also mutually perpendicular to z axis. So in py case also, so that means you get pi px and pi py orbitals. ये दोनों same ही होंगे. ये pi px मान लो या pi py मान लो, it's one and the same thing. Got it? Now if I talk about the positive combination, I should also be talking about the negative combination. So the negative combination will be, ये तो हमारा normal px हो गया, alright, minus of the px of the other orbital. So now in this case minus sign आ गया तो इन दोनों के signs change हो जाएंगे. So minus की वजह से now this will become minus and this will become plus. Now you have, it is sideways overlap only. So this will again be pi, this will be pi and this will be anti-bonding. So pi star 2px or pi star 2py. So py will behave in a similar fashion. So I am not doing it for py again. What is the significance of psi operator? Is there any significance of psi? Is there any significance of psi? No, there is no physical significance of psi because it can be either real or imaginary. You can attach significance to psi only if you multiply it with its complex conjugate. Okay, and then ma'am, will there be any combination of two different orbitals like 1s and 2p? We can talk about the combination of 1s and 2p also because as it is we have seen that when you talk about the methane molecule, then in that case you have the hydrogen atom, that means 1s is interacting with px also and py also and pz also. So that is the interaction of 1s and 2p, right? So now coming back to this, we are talking about molecular orbital theory and px and py both will have a sideways overlap. You have understood that the positive sign will be taken in the increasing direction, negative in the opposite direction. दोनों को combine करेंगे, once in a positive fashion, once in a negative fashion. So दो atomic orbitals के combination से what you get is a molecular orbital. So you have the combination of two atomic orbitals resulting in a molecular orbital. Alright, and that molecular orbital will either be bonding or anti-bonding. Remember that the total number of molecular orbitals will always be equal to the total number of combining atomic orbitals. जितने combining atomic orbitals होंगे उतने ही आपको जैसे how many atomic orbitals are here? You have two atomic orbitals here, one for the px and the other for the px of the other. So how many molecular orbitals are you getting again? Two. One is the bonding and the other is the anti-bonding. Now coming on to the pz orbital. Now for PZ. PZ is located about the internuclear axis. PZ is about the internuclear axis. So here, this is my PZ. If I consider this to be the internuclear axis like that, and PZ will be, now what, if PX plus PX is pi PX, what will be PZ plus PZ? ऐसे बिना सोचे बोलोगे, this is what I was checking. What we have is, in PX plus PX, we have a sideways overlap. But PZ and PZ both are located about the internuclear axis. So there will be a direct overlap. So it will be sigma. One thing is that. And then another thing, PZ में एक और difference है that whenever you have a positive linear combination, एक PZ मान लो एक atom का PZ इधर है, the other PZ is like this. Alright, it should be symmetrical. देख लेना. Don't go by the diagram. So this will be negative, and what will this be? Positive, increasing direction. This will be negative, and this will be positive. So this is your PZ, psi of PZ, and this is your another PZ of some other atom. Now in this case, PZ plus PZ will give you sigma PZ, but will that be bonding or anti-bonding? That will be anti-bonding. So in this case, your psi of PZ plus psi of PZ, you have positive interacting with the negative sign. And what did I tell you? Whenever a positive interacts with a negative sign, you will always get anti-bonding. So in this case, it will be a sigma PZ, that will be star. That is sigma PZ anti-bonding. And what will be the resultant orbital? It will be negative. Then you have a positive. And then you have a negative, and you have a positive. So how many nodes? You will have 3 nodes here. 1, 2 and 3. ठीक है? Clear to everyone? And then just check it out for PZ of minus of PZ minus PZ, psi of 2PZ say minus psi of 2PZ of the other atom. So this will be negative positive, and now minus of negative positive, this is your one PZ, this is your another PZ. One was a positive linear combination, now you have a negative linear combination. तो इस minus की वजह से ये sign क्या हो जाएगा plus, और ये sign हो जाएगा minus. So now in this case what do you have? This is your sigma star PZ. This is your now negative linear combination, and you have the positive interacting with the positive. You know that PZ plus PZ is giving you a sigma, and you have the same signs now overlapping with one another, interacting with one another. So in this case you will have a sigma PZ bonding, and your resultant molecular orbital will look something like negative, positive, negative. ठीक है? As simple as that. There was hardly anything to understand in this. Again, how many atomic orbitals do you have? Psi of 2pz of A and psi of 2pz of B. दो atomic orbitals हैं, तो कितने molecular orbitals बन रहे हैं? एक sigma pz bonding and एक sigma pz anti bonding. So two atomic orbitals are yielding two molecular orbitals, one of which is bonding in nature and the other is anti bonding in nature. ठीक है, समझ में आया? Clear to everyone? Now a quick recap of the molecular orbital theory that we have just started today. In molecular orbital theory, one thing that you have to remember, that quantum mechanically each electron is associated with all the nuclei. This can be put in very many languages, that your electron is moving under the influence of all the nuclei. Each electron, alright, and when they are independent and associated only with their own atom, it is your valence bond approach. Okay, now when we are talking about the molecular orbital approach, I stated that the number of molecular orbitals, will be equal to the number of combining atomic orbitals. Alright, number of atomic orbitals. Now here in this case, when I stated that 1s plus 1s, this is what we did. There will always be a positive and then you can have a negative combination. So अगर मान लो ये हाइड्रोजन एटम की मैं बात करूं, please now look up carefully onto the board. I am talking about hydrogen atom A and hydrogen atom B. What is the configuration of hydrogen atom A? It is 1s 1 and this will also be 1s1. Now these are my atomic orbitals क्योंकि इसके बाद फिर 2s आएगा फिर 2p आएगा and so on. Now if, and that is the order of energies also. So if 1s and 1s combine, you know that they are yielding once your sigma bonding and once your sigma anti-bonding, and out of which bonding is more stable and anti-bonding is less stable. So bonding will be lower in energy and anti-bonding will be higher in energy. What is the characteristic feature of the bonding molecular orbital is that both of these now will be combining to form your bonding molecular orbital, that means sigma 1s, and once it will form your sigma star 1s. Remember that the energy of the bonding molecular orbital will always be lower than the two combining atomic orbitals. Bonding will be more stable and anti-bonding will be less stable than either of the two. So in that case the bonding will always be lower than either of the two combining orbitals and the anti-bonding will be higher in case of higher than either of the two atomic orbitals. Clear with that? Now just look up onto the board again. ये बहुत simple example है, let's just discuss it quickly. You have one electron and so two atomic orbitals combining to form your molecular orbitals. तो इधर इधर क्या है हमारे atomic orbitals, center में क्या है हमारे molecular orbitals. How many electrons? 2. Both of them will start occupying from the lower level now. So both the electrons will go into the sigma 1s. So the electronic configuration of hydrogen molecule will be sigma 1s2 and sigma star 1s में 0, क्योंकि 1s में तो है, sigma star 1s में नहीं है. And from here we can easily find out something which is called as the bond order. Remember that the bond order is nothing but half of number of bonding electrons minus number of anti-bonding electrons. Now इसमें number of bonding electrons कितने हैं? 2, क्योंकि दोनों bonding molecular orbital में है, anti-bonding में 0 है, तो this will be half into 2 minus 0, that will be equal to 1. And there is another way of defining the bond order. Bond order is nothing but the number of bonds which are getting formed, right? It is just the number of bonds which are getting formed. Like for example, if I talk about the bond order of CO, so the bond order is 3. I talk about the bond order of O2, 2. ये आपको Lewis structure से पहले ही पता है. Bond order is nothing but it is the representation of the number of bonds between the two atoms. And it can be in decimals also, it can be 1.5, 2.5 also, we'll just see how. That you can designate easily from your molecular orbital method. Clear? तो इस केस में Lewis structure आपको बनाना आता है. I hope you remember. Like for oxygen, how many valence electrons do you have? 6. So you have 6 valence electrons, and when you actually combine them, whatever is like being shared, so you join the two, and then you know that this is forming a double bond, which means that the bond order will now be 2. Clear with that now? ये चीज समझ में आ गई. I repeat it again. The two atomic orbitals are combining to form two molecular orbitals, and when it forms the molecular orbitals, it will form two molecular orbitals, one of which will be bonding in nature, lower in energy, the other will be anti-bonding in nature, higher in energy, and you can easily find out the bond order. Bond order is nothing but half of number of bonding electrons minus number of anti-bonding electrons. Bonding electrons मतलब जो हमारे bonding molecular orbital में है, anti-bonding मतलब जो anti-bonding molecular orbital में है, and half of that will give you the bond order. Now bond order is the number of bonds, so H and H will have only a single bond. Now another thing is that in this case, remember that the bond order is directly proportional to your bond energy. तो जितना ज़्यादा bond order, higher will be the bond energy and more will be the stability. You getting the point? Bond energy means it is the energy required to break the bond. So in this case, bond order is directly proportional to bond energy, and you know it should be inversely proportional to bond length. क्योंकि जितना छोटा bond length उतना it will be difficult to break your bond, so higher will be the bond energy. So remember that bond order is directly proportional to bond energy is inversely proportional to bond length. Why anti-bonding is less stable? Anti-bonding is less stable as you have seen the initial, that is why I took up the basic part, that whenever you have the opposite signs interacting there will be less stability. Whenever you have the same signs interacting there will be more stability. Like if you were interacting with a person of your level, you will be able to interact more and there will be greater stability than interacting with a person who does not carry the same views. So it is like that. So positive and a positive results in a bonding orbital, which will be less in energy means more stable, and a positive when it interacts with the negative energy, it's like the opposites are interacting now, so it will be a higher energy and less stable. Please draw the diagram for sigma px and sigma px interaction. I am using this place to draw the sigma px and sigma px. Okay. So now in this case, say px, it will be a positive sign will be in the increasing direction and negative sign will be in the other direction. Px plus a px. Okay. Px plus a px will be, now this is px and this is again px. I am saying z is the internuclear axis. So naturally it is not located about the internuclear axis. So there will be sideways overlap. Sideways overlap का मतलब है that this will result in a pi bond formation, and because the same signs are interacting, plus is interacting with a plus to form a plus, the negative is interacting with a negative to form a negative orbital. So this will be like same signs when they interact, you have a bonding molecular orbital. So this will be a sigma bonding. Okay. Now in the other case I told you एक बार positively interact करते हैं, एक बार negatively. तो जब negative sign यहाँ पे आ जाएगा, तो now when you have a px minus of px, so then in that case what will happen? This minus will change the signs of the lobes. So this will become minus, यहाँ से हटा दो, this will become then minus and this will become plus. So now you have again the sideways overlap, so which means that a pi bond is getting formed and a plus interacting with a minus. So opposite signs are now interacting, so this will result in an anti-bonding molecular orbital, and the resultant will be something like this. You will have 4 lobes which are different, plus interacting with a negative and a negative interacting with a plus. So this is sigma star and for your px. Okay. Can you please draw the Lewis structure of H2SO4? We'll talk about the Lewis structure once we complete off with our molecular orbital theory. That's like a little off the topic. इस केस में जब px और px are located, see this is our internuclear axis, okay, and you have your px located like this and you have your px located like this. Alright, so in this case you have the plus sideways interaction. अगर px, if x was the internuclear axis, फिर वो ऐसे it would have been about the internuclear axis. तो जब direct overlap होगा, when they will be like about the internuclear axis, then in that case you get a sigma bonding. But when they are like not touching each other, but rather there is like a sideways overlap, then in that case it is a pi. Ma'am, why are we adding and subtracting the atomic orbitals? See, there are always 2 ways of interacting. Either you talk to me normally or you start fighting with me. So there is always a positive interaction and a negative interaction. So these are the only possibilities which are there. So that is why we add and we subtract once. It's just analogous to your macroscopic world. Both are taking place always. Whenever we are talking about the interaction of the atomic orbitals, we are talking, and all this is like what? Atoms are microscopic entities. All this is a probability. So we are going on the case of assumption. We are assuming, and then the final result turns out to be correct. You getting the point? अगर कुछ assume करके चलना है, say if I have to guess, as I stated, the weight of this table, I may say that the weight is 10 kgs. If it turns out to be 10, I will be happy and I will say whatever I assumed was correct. So then in that case I'll start guessing things, guessing onto other things as well, because then you feel that there is like some kind of a mark. So what we do is we take a positive and a negative combination based on our hypothesis, and then finally the results also turn out to be well. No, then you will have, one was the pi px and the other is the pi star px. So then you have the combination. आपके दो atomic orbitals थे, px of one and px of the other. दो atomic orbitals. अब उनके combining style are two. One is a positive which will give you a bonding molecular orbital, and the other is the negative which is like anti-bonding molecular orbital. Alright. So I mean what we have seen, if I'll summarize it quickly after this. First let's talk about the hydrogen atom first. In hydrogen atom, what did we see? That we have a 1s combining with the 1s to give you the bonding molecular orbital 1s, and you have an anti-bonding molecular orbital. Clear with that? Both the electrons will come in the lower energy state, and bond order will be equal to half of 2 minus 0, that is equal to 1. So now what will be the bond order of H2 plus? What will be the bond order of H2 plus? Plus means one electron has gone, so it will be, for H2 plus, the bond order will be half of 1 minus 0, that will be equal to half. So H2 plus will be less stable or more stable than H2? See, in this case the bond order is now 0.5. Bond order of H2 was 1. So lower the bond order, lower is the stability. So you know that bond order of H2 is like greater. So in that case H2 is more stable than your H2 plus. Then there is a question. Now I am giving a question to all of you and you tell me the reason. Why is He2 not possible? H and H form H2. Why is He and He not forming He2? Why is helium 2 molecule not possible? Now you do not have to actually draw the molecular orbitals at all times. See, you have He and He. What is the configuration of He? 1s and 1s. 1s2 and 1s2. You know 1s is combining to give you a sigma 1s, and it is combining to give you sigma star 1s, right? And in this case now you have 4 electrons in total. You will consider the total number of electrons and then start filling. So what will be the total number of electrons? 2 here and 2 will go here, because not more than 2 electrons can be accommodated in any orbital. So what you have is 2 here and 2 here. So in this case what is the bond order? Bond order is half of number of bonding electrons, that is 2, minus minus number of anti-bonding orbitals, that is also 2, so that is equal to 0. So 0 bond order means that it is highly unstable molecule and it will not get formed at all. Similarly, this question is also put for neon 2. For it also the bond order is 0. We'll just look into it now quickly. Now say if you have to talk about, now look up here, this is your 1s, then you can have similarly 2s orbital also, right? And you will have your 2p orbitals also. That is how the order goes. You will have 2p orbitals also. You have your 1s, right? Now in this case what you have is in this case you have 1s, 2s and 2p. 1s and 1s will form sigma 1s and sigma star 1s. Alright, this is one which is lower in energy, so I had drawn it lower. Then 2s will form sigma 2s and sigma star 2s. I want each one of you to look onto the board. Okay? And then you have now p is combining. Now 3 plus 3, 6. So we should get 6 molecular orbitals only. So here what you have is, you have the pi px and pi py located lower in energy than your sigma. Because of course pi px and pi py will have similar energies, because both are interacting in a sideways fashion and both are yielding your bonding and anti-bonding molecular orbitals in a similar fashion. Px and py ka diagram was also same if you remember. So then in that case what will we have? We will have pi 2px and pi 2py lower in energy than your sigma, and sigma will be like sigma 2pz. Clear with that? Now again here you will have pi orbitals, then anti-bonding. So you will have pi star px and pi star py, they are like degenerate, and then you will have your sigma star 2pz or sigma star pz. Now there is very important thing. Now if I move on to now higher atoms where you have the p orbitals also getting filled up, let's take up the example of C2. Let's take up the example of C2. All of you all look up onto the board. C2, in C2 what do you have? How many electrons? 6. So 1s is also there. So 1s2, 2s2 and 2p2. This is your carbon 1. And again here you will have 1s2, 2s2 and 2p2. Right? Now calculate the total number of electrons. The total number of electrons are like 4 here. So how will they get filled? 1, 2, 3 and 4. Lower first and then higher. Now here what are the total number of electrons in p orbitals? 4. So here what will happen is, first it will take care of these two degenerate px orbitals, because you know according to Hund's rule of maximum multiplicity, if this is px and this is py, according to Hund's rule of maximum multiplicity, each orbital of similar energy will get filled first and then pairing will start. So these 4 electrons will be 1, 2, alright, 3 and 4. Clear with that? And so your sigma 2pz will be 0. And what will be the bond order? You can easily calculate half of number of bonding electrons minus number of anti-bonding electrons. इस केस में अगर 1s को भी मानते हो, initially let's check it up. So 1s will also be this. So how many number of bonding electrons? 2, 4, 6, 8. Minus how many number of anti-bonding? 4. So that will be equal to 4 by 2, which is equal to 2. Got it? And similarly you can easily find out for now N2. Now I am asking you to write down. And how do you write down the molecular orbital configuration? Like for N2, you will be writing sigma 1s2, sigma star 1s2. Then you will have sigma 2s2. Then you have sigma star 2s2. How many electrons total? You have 7 plus 7, 14 electrons. Sigma is stronger, but when you interact with, when you make them interact, it is the pi orbital which lies lower in energy for px and py. I will just come to this point also again. Please now here remember that sigma followed by sigma star 1s, then you have sigma 2s followed by sigma star 2s, then you have pi px and pi py, pi 2px and pi 2py to be similar in energy. That will be like, you'll just fill it up, and then you have sigma 2pz next, then you have pi star 2px and you have your pi star 2py next in energy, and then you have sigma star 2pz. Okay? The total number of electrons are 14. So let's fill up these 14 electrons. It will be what? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. So how many electrons taken care of? 8. How many left now? 6. So 2, 4, 6. Done? This is the order of filling of the atomic orbitals, molecular orbitals according to the increasing order of energy. Now here, अगर ये 1s है, ये भी 1s है, you have 2 electrons and 2 electrons here. So now for nitrogen it will be 1s sigma 1s2, sigma star 1s2, because what is your N? N is 1s2, 2s2, 2p3. Then again you have another nitrogen which is 1s2, 2s2 and again 2p3. Clear with that? It is 1s2, 2s2, 2p3 again. So your 1s and 1s is combining to give you what? Sigma 1s and sigma star 1s. Sigma star 1s is higher in energy. Then this is going to give you sigma 2s and sigma star 2s. So 4 and 4 electrons will be taken care of here itself. Alright, and then comes your p orbitals which will have a total of 6 electrons, and those 6 electrons will be like, first this was the atomic orbitals, px, py, pz all are degenerate. ये या तो ऐसे books में बना होगा या ऐसे. If they lie close enough, then that means we are talking about degenerate orbitals only. What are degenerate orbitals? The ones which have similar energy states at the same energy level. So in this case, this is 3. So 3 plus 3, 6. So 1, 2, 3, 4, and now 5 and 6. Got it? And what will be the bond order? Now the bond order in this case will be what? Now see, bond order is half of number of bonding electrons minus number of anti-bonding electrons. What is that? Now number of bonding electrons is 2, 4, 6, 8, 10. Alright? Minus number of anti-bonding electrons will be 2 and just 4. So it is equal to half of 10 minus 4, that is equal to 3. ठीक है? इसका एक और तरीका है कि आपको पता है 1s and sigma star 1s are like will be cancelling each other. 2s में 2s में तो ये inner shell orbital हो गया, 2s के भी 2s में तो cancel हो गया. So you just look on to the final वाला orbital which is getting filled up. You can also do it as half of number of bonding electrons in the final orbital, that is 2, 4 and 6. So 6 minus 0. So that is equal to 3 again. Got it? There are ways of doing it. If you can just write down the final configuration. ठीक है? Now tell me the bonding orbital for N2 plus and N2 minus. Once you do not need to draw the diagram again, just take it out from the orbitals. N2 plus means an electron is added to the anti-bonding molecular orbital now. N2 minus means, sorry, N2 minus, agar if I am putting a minus, minus means what? It has taken up an electron. So that electron will come to the anti-bonding. So for the case of N2 minus, it will be half of 6 minus 1. 6 minus 1 now. क्योंकि anti-bonding में एक add हो गया ना, तो that will be 5 by 2, that will be 2.5. And अगर N2 plus का अगर हम देखेंगे, that was 3 initially. N2 plus means now 1 electron has gone away from here. So then that means it will be half of 5 minus 0, that is again equal to 2.5. So you should be able to find out the bond orders quickly because the bond order trend is asked in the examinations. Entrance examinations, bond order trend, and subjective paper anything. Yes. Kind. That is like an indication of the number of bonds. Now N2 is like 3 means you have N, triple bond N, right? Now when it acquires a negative electron, then in that case it gets destabilized by a certain extent, because of which there are bonds which are getting destabilized. So this will be negative. And how will it acquire a negative charge? Maybe by the shifting of electrons. So that shift of the electrons is not complete. It is like only 0.5 of the bond is getting shared. देखो एक चीज मैंने आपको बताई थी, if you are talking about two bonds, this is only the answer to your question. So if the complete bond is getting transferred, this becomes A plus and this becomes AB minus. अब only a minus charge is acquired. So in that case, maybe the bond is not getting, it is like this. Okay, maybe one electron goes to this and one electron goes to this. Then in that case it becomes A, and you have one bond here and the other electron here. So it all depends. So it is like a partial shifting of the bond. So this is like 2.5. Bond order in some, no, bond order will be only a positive entity because you are talking about the interaction of bonds. If it is negative, then it will be unstable. जब zero में ही the molecule is not getting formed, how can you think about the negative one? Okay. Then next, here done. Yes. Please tell us the relation between stability, bond order and energy. Greater the bond order, greater will be the energy, greater will be the stability only. Can bond order come in decimal? Yes, we have just seen bond order comes in decimals as well, where we can say that now the stability of N2 plus and N2 minus will be equivalent. You can get any. I have just taken some hypothetical cases. So the bond order of N2 plus and N2 minus is same, and for nitrogen it is the highest, which means that nitrogen is in itself very stable. So now वो N2 plus बनना चाहेगा ना N2 minus. So it will tend to become. What is the bond order of benzene? Now for benzene it is like C6 and H6. In that case you talk about the resonance hybrid structures, and we shall not exactly lay emphasis on the bond order. We will come to resonance after completion of this, that we had taken up once before also. So that is why I put it on an end. Please explain the p orbitals again. p orbitals means that whenever px and px combine, you get a pi px, and whenever p pi and p pi combine, you get a pi py. Whenever a pz and a pz are combining, then you get a sigma pz and a sigma star pz. Is that much explanation sufficient, or you want me to draw the orbitals again? I am coming to it. Now just look. See, whenever we have the combination of the sideways overlapping here, okay, sideways, whenever a bond is formed, energy is released. In this case, the bond is formed to a greater stable extent and it releases more energy, it goes higher in energy. And in case of pi, it is like a sideways overlap which doesn't interact so much, so it lies lower in energy. Now, coming to one of the major points as to what decides whether this sigma is going to remain up and this pi is going to remain low. Look up onto the board, this is an important explanation. Till your nitrogen, your sigma lies above pi. ठीक है? क्यों? क्योंकि basically orbitals of similar types interact with one another. This is like a law of nature. Similar type of things interact with one another. Orbitals of similar energy. That means S is located about the internuclear axis. Sigma pz is also about the internuclear axis. So this S tries to interact with this sigma pz. ठीक है? तो होता क्या है? Till nitrogen, the difference in energy between 2s and 2p is not that much. They are close enough such that this S can easily interact with this sigma 2pz. Correct? This S wants to interact with sigma 2pz. ठीक है? अब इसको interact करना इसलिए easy है because till nitrogen the atomic orbital difference, energy difference is less between 2s and 2p, so sigma is lying sufficiently close as it is. So we don't need to bring about any changes to pull sigma down. Got it? So that is why till nitrogen N2 molecule, what you have is you always have the pi getting filled up first and sigma getting filled up later. So the order of p orbitals is pi, sigma, pi, sigma. This you can remember. Pi will be pi px and pi py and sigma pz. Then you have pi star px and pi star py and sigma star pz. Now what happens when it goes beyond the 14 electron level? You have, see, oxygen now. ठीक है? Oxygen is what? It is 8 plus 8, 16 electrons. Oxygen is 8. It is 16 electrons. Now here what happens? The orbital energy difference increases. That means this 2p shifts a little higher in energy, which will take the sigma and pi also up. Right? So now it becomes difficult for this S to interact with sigma, because this S wants only sigma to interact with, it doesn't want any pi molecular orbital. Is that thing clear to everyone? Now this S, because it wants to interact with this sigma and it has gone higher in energy, what happens as a result of that? It pulls the sigma lower in energy and pi px and pi py are shifted up. So then you have pi px and pi py up and you have sigma 2pz shifted down because of this interaction which it wants to do. This interaction of S with P is known as sp mixing. It is known as sp mixing. So what happens till nitrogen? Till nitrogen is nitrogen tak S and P ka difference, the orbital energy difference was very less. And because the orbital energy difference was less, तो जो जहाँ पे था उसको वहीं रहने दिया, because S could easily interact with sigma. So the order of filling for the p orbitals was pi, sigma, pi star, sigma star. ठीक है? Clear with that? Now what happens after nitrogen? The orbital energy difference between oxygen 2s and 2p, it increases drastically. अगर 2p atomic orbital ऊपर shift हो गया तो molecular orbitals would also go higher in energy, and if they go higher in energy, the sigma will be shifted more up. Now it was difficult for sigma to interact with 2s. So because of the interaction of sp, what it does is it pulls that sigma lower in energy so that now it can interact well. So what happens after nitrogen is that from oxygen itself you have the filling of the sigma 2pz first and pi 2px and pi 2py later. But if say if there is like a big class only the first two students are talking. Will the last students get affected because of that talking? No, they will remain as it is. So if the interaction of this S is to be with this P, so then in that case this order remains as it is. So here sigma star is not pulled down. Here it remains as, so therefore from oxygen onwards the filling of orbitals happen as sigma pi pi sigma. Alright, पहले क्या था pi sigma and then it becomes sigma pi pi sigma. Clear? Now you tell me what will be the इसीलिए, and earlier there was no need because your S and 2p were sufficiently close to one another such that the energies as they were coming by the combination of the atomic orbitals remained as it is. But one is the first shell, second is altogether a different shell. So principal quantum number का difference है 1 and 2 are high, there is the energy gap is large. So that is why that interaction is not taking place there. It's a very good question. The question is, if the similar type of orbitals are interacting with one another, if this S is wanting to interact with this sigma, this 1s will also try to interact with sigma 2ps, sigma 2s, but why does it not interact? Because this is like first shell and this is altogether a different shell, so the energy gap is more, so it will not interact. But here in case of 2s and 2p, they are the subshells of the same principal shell. The interaction is like a possibility which is because of similar factors giving it more enhanced properties. Like the interaction is always, it's like a natural phenomena which is occurring, and you can give reason to, you get to, I am telling you S interacts only with sigma. Why? Because you will say that they are of the similar types. S would not prefer to interact with pi. फिर interaction कराना ही है तो सबके साथ friendship कराए ना उसकी. But it doesn't prefer to interact with pi because they are of different orientations and different types, not about the internuclear axis, and it becomes difficult also. एक ऐसे orbital है, एक ऐसे orbital है, so it becomes difficult for this to interact with this type of an orbital. But if both of them are like this, they can easily interact with one another. This is another orientation, energy, all of these things are taken into consideration.
In that till nitrogen we have 2p and above. Since sigma naught is more stable, so it should be lower.
This is the question that she asked. I stated that this is only because of the reason that when your atomic orbitals, molecular orbitals are formed, it is the combination energy which matters at that time. एक नाइट्रोजन और एक नाइट्रोजन आप साथ में कंबाइन कर रहे हो, तो when they are combining, it is the resultant energy of the resultant molecular orbital which will decide whether sigma will lie lower in energy or higher in energy. It's purely a phenomenon of what is occurring, and in that case sigma lies higher in energy. But why is it pulled lower later is like one reason that we can think of is that due to the sp mixing it needs to interact, so it pulls it lower in energy. Otherwise sp mixing is happening in all the cases. Clear with that? So what is the, now you tell me the order of energy, order of bond length, these questions you will find in many books. Order of stability, all right, and bond order, okay, for O2, O2 plus, O2 minus, O2 2 minus, and O2 2 plus. Find out the order for the bond order and for the energy, bond length, stability, all. So all you have to do is just write down the molecular orbital configuration, fill up all these levels, and then you just have to put the order. Then it's like a simple cakewalk. Questions. Why there is an increase in the energy level in case of O2? See, as we move higher in energy, this is like what has been experimentally determined from spectroscopic studies also, that the orbital energy difference becomes high, more and more. with increase in atomic number. So till atomic number 7, when the atomic orbitals combine, the difference between 2s and 2p is like okay, close to one another. But beyond the atomic number 7, what happens is atomic orbital energy difference between 2s and 2p becomes large enough. So that is the reason. Why is there an increase? That's done. Then why the energy of sigma molecular orbital is greater than that of pi molecular orbital? See, in cases like, this is what was a question that was just put. In cases like for till nitrogen, whenever the two atomic orbitals are combining, it depends upon what is the energy which is released or absorbed when the atomic orbitals are combining to form a molecular orbital. So in that case, the energy involved in case of sigma is more than the energy involved in case of pi, and that is why it lies higher in energy. And precisely that gets reverted or reversed in case of molecules which go beyond the N2 level. So the order is reversed in that case, and one more reason added up to that is the sp mixing, which pulls sigma lower in energy. When the bond order is diamagnetic and paramagnetic, I will just explain that now. Done with oxygen. How many electrons now? 16. Let's check it up. 2, 4, 6, 8, 10, 11, 12, 13, 14, 15 and 16. Is that the case? Right? 2, 4, 6, 8, 10, 12, 14 and 16. Done. The electronic configuration that you all must have written is sigma 1s, sigma star 1 is, sigma 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2, sigma 2pz 2. Then you have pi px and pi py, because now sigma will get filled first. So sigma 2pz 2, then pi px 2, pi py 2, and pi star px 1, pi star py 1. Because according to Hund's rule of maximum multiplicity, each orbital will be singly filled first, and then pairing will begin. Now for the bond order of normal O2, that will be half of number of bonding electrons. Let's look up only in the p, because नीचे वाले तो सारे totally filled हैं. So that will be 6 minus 2, 6 minus 2 in pi star px and pi star py. So that will be equal to 4 by 2, which is equal to 2. So the bond order of O2 is 2. What is the bond order of now O2 plus? O2 plus means one electron has been given from the anti-bonding orbital. So that will be equal to half of 6 minus 1. So that will be 5 by 2. So that will be 2.5. So O2 plus will be 2.5. Now O2 2 plus means that 2 electrons will be given away from the anti-bonding molecular orbital. So it will be half of 6 minus 0. So that will be equal to 3. Now O2 minus means 1 electron is added to the anti-bonding molecular orbital. O2 minus means 1 electron is added to the, कहाँ आएगा, जहाँ पे जगह होगी वहीं आएगा ना. So it will be half of 6 minus 3 now. So that will be 1.5. And now 2 electrons getting added, that will be 6 minus 4. 2 electrons being added means 6 minus 4. That will be 2 by 2. So that will be 1. One conclusion that you can draw from here is, whenever an electron is removed from the anti-bonding molecular orbital, it becomes more stable. The molecule becomes more stable. Whenever an electron is added to the anti-bonding molecular orbital, it becomes less stable. Okay? Please make it a point, because this generalized statement can also be asked. Whenever an electron is added to the anti-bonding molecular orbital, it gets destabilized. Anti-bonding means it's destabilizing. Whenever an electron is removed from the anti-bonding molecular orbital, the molecule gets stabilized. The orbitals get stabilized. ठीक है? Now look at the trend now. The bond order trend is O2 minus is less than O2, O2 2 minus is less than O2 minus is less than O2 is less than O2 plus is less than O2 2 plus. So the bond order trend is like this. Greater the bond order, greater will be the bond energy. So the bond energy trend will also be the same. Bond length trend will be the reverse because they are inversely proportional, and that means O2 minus will have the highest, O2 2 minus will have the highest bond length with the least stability. So O2 minus, O2, then the stability follows the same order as your bond order, right? It follows the same order. So the highest energy will be that of O2 2 plus. Highest stability also O2 2 plus, because here the energy is not the energy that we talk about. We say that whenever the orbital energy is low, we say that is more stable, because ऐसे कई बच्चे confuse हो रहे होंगे. Whenever we say that the orbital energy is low, that means it's lying lower in energy, it's stable. ठीक है? But bond energy ज़्यादा होने का मतलब it's a bond which is getting formed. Now what is the energy which is required to break that bond? समझ में आया? ये वो वाला नहीं है कि एनर्जी लो है कि ज्यादा है. वी आर नॉट टॉकिंग अबाउट द ऑर्बिटल एनर्जी, वी आर टॉकिंग अबाउट द बॉन्ड एनर्जी. सो दिस इज काइंड ऑफ अ बॉन्ड which is formed and the energy which is required to break the bond. So the highest bond energy is in case of O2 2 plus, and that is why that is the most stable, because you require a lot of energy to break the bond there. ठीक है? Now then just quickly do it for Ne2, neon 2, and tell me what will be the bond order for Ne2. Ne2. You can straight away fill up the electronic configuration also. You know the order. Now you know sigma 1s, sigma star 1s. Then you know it is sigma 2s, sigma star 2s. Then after oxygen, after nitrogen, starting from oxygen itself, you know that sigma gets filled first. So the order is sigma pi pi sigma. So you have sigma 2pz, pi 2px and pi 2py. Then you have pi star 2px, pi star 2py, and you have sigma star 2pz. ठीक है? And neon means 10 electrons in 1. So a total of Ne2 में कितने होंगे? 20 electrons. 20 electrons means 2, 4, 6, 8, 10, 12, 14, 16 and 18 and 20. So the bond order in this case will be half of 10 minus 10, which is equal to 0. And again, because the bond order is 0, there is no possibility of the Ne2 getting formed. Okay, now when you look up in this case of just the 2p, in this case you have sigma, okay, and then you have pi, and then again you have pi star sigma, and you have sigma star. All the electrons are paired up, right? All the electrons are paired up. When all your electrons are paired up, it is a diamagnetic molecule. When all electrons are paired up, it's a diamagnetic molecule. And when some of the electrons are like as in case of, you tell me whether O2 molecule is diamagnetic or paramagnetic. Why? How many electrons? 2 electrons are unpaired. In which orbital? Anti-bonding orbital. You have pi star px1 and you have pi star py1. So because 2 electrons are left unpaired, so that is why you say that it is paramagnetic in nature. Whenever you have even a single electron which is left unpaired, then you say that the molecule is paramagnetic. Tell me whether N2 will be diamagnetic or paramagnetic quickly. This answers the question, one of the questions that was put up. N2 will be diamagnetic. 14 electrons. You know that it is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2p, 2s2. Then you have pi 2p x2, pi 2p y2, sigma 2p z2, and the rest are all zeros. So all are paired up. So it is like a diamagnetic. Sorry, because all are paired up. Okay, and remember that here also the order of filling is like similar to that of it follows the Aufbau's principle. What is Aufbau's principle? States that the electron will be filled up according to the increasing order of the energies of the orbitals. Yes.
Can we find out which is diamagnetic, paramagnetic using both?
You can in case of 0.5s it is generally yes single, so you can relate it to that. Yes, you can relate. All right, then another thing. Now I'm asking you to draw. Now please look up onto the board now. This was all for the homonuclear diatomic cases. What have we done? We have done the molecular orbital treatment only for homonuclear diatomic molecules. Homo means same, nuclear means जो भी atom की बात कर रहे हो आप, homonuclear. Diatomic means only two atoms, diatomic molecules. This we have done. Like you can talk about H2, you can talk about He2, you can talk about so on till N2, then you have O2, and then you can talk about Ne2 and further on. So all these are what? These are like two atoms of the same type are combining with one another, and then we are doing it. Now we'll just look into the molecular orbitals for heteronuclear diatomic molecules. Like for example, you will have NO, CO, etc. These are like one of the most important examples that are generally taken up and asked in the examination every year. Every year almost there is a question from heteronuclear diatomic cases which are like NO and CO. These are the favorite two molecules. Now just look up onto the board. The one thing, you know now here there was no electronegativity difference. All of them had no electronegativity difference, whereas in this case of NO and CO there is an electronegativity difference where oxygen is more electronegative than nitrogen, and in case of CO it is more electronegative than carbon. इस केस में क्या होता है? The one which is more electronegative will have its atomic orbital lying lower in energy than the other. अभी तक हम क्या कर रहे थे? हाइड्रोजन हाइड्रोजन कंबाइन कर रहे हैं तो दोनों का एक का 1s इधर है तो दूसरे का भी सेम लेवल पे है. लेकिन when you talk about the combination of 1s of nitrogen with 1s of oxygen, this will lie lower in energy than your 1s of nitrogen. Remember that the atomic orbitals of more electronegative elements are lying lower in energy. ठीक है? They are lying lower in energy. इसका एक reason भी है. अगर जनरली सोचो, अब तो एनर्जी की हम इतनी बातें करते हैं, नाइट्रोजन इज लाइंग, आई एम सेइंग मोर इलेक्ट्रोनेगेटिव एलिमेंट इज लाइंग लोअर इन एनर्जी. व्हाट इज इलेक्ट्रोनेगेटिविटी? इट इज टेंडेंसी टू एक्सेप्ट इलेक्ट्रॉन्स, और इलेक्ट्रॉन सबसे पहले किस में आएगा? लोअर एनर्जी ऑर्बिटल में. तो इलेक्ट्रोनेगेटिव मीन्स इट इज द टेंडेंसी टू गेन इलेक्ट्रॉन्स. इलेक्ट्रोनेगेटिव एटम विल कीप इट्स एनर्जी लेवल low so that it can easily gain or accept electrons. So remember that the oxygen which is more electronegative will have all its atomic orbitals lying lower in energy in comparison to nitrogen. एक चीज तो ये है. दूसरा, the rest of the diagram, molecular orbital diagram looks exactly the same. See, if you have what is nitrogen? It is nitrogen is 1s2, 2s2, 2p3. What is your oxygen? It is 1s2, 2s2, 2p4. And what about carbon? Is like 1s2. So 2, 4, 6. Let's talk about carbon monoxide first. Please, let's talk about carbon monoxide before nitric oxide. Carbon monoxide. Please look up. Carbon is like You have carbon as 1s2, 2s2, 2p2. What is your oxygen? How many electrons in carbon? 6. How many in oxygen? Total of? Right? 8 and 6, na? So total of 14 electrons. In homonuclear diatomics, which had 14 electrons in total? Nitrogen. N2. What was the order followed in the p orbitals for that? It was pi, sigma, pi star, sigma star. Pi orbital was getting filled in till nitrogen. So the same order will be followed for carbon monoxide. ठीक है? ये बात समझ में आई? Are 14. Whenever you go beyond the level of 14, your sigma will be pulled lower in energy. ये याद रखोगे? I am not going into the in-depth analysis of why, who, this, that. An open explanation has been given. Now, beyond 14 electrons, your sigma will always be pulled lower in energy. So, what are the total number of electrons in case of carbon monoxide? It is 14. So, the order of filling will be the same. You can draw the energy level diagram, but what will be the 1s, sigma star 1s? What will be the order of filling? It will be sigma 2s, sigma star 2s. Then you will have pi 2px, pi 2py. I am writing them together because these two are degenerate. Then you have sigma 2pz. Then you have pi star 2px, pi star 2py, and you have sigma star 2pz. What are the total number of electrons? 14. So it will be the same 2, 4, 6, 8, 10, 12, 14. ठीक है? What will be the bond order for CO then? Same है electronic configuration, so it will be 3, and that is why your carbon monoxide is also represented as this. You get this from Lewis structures also, you get it from VBT also, and you get it from now MOT also. So now you are seeing that the approach is different in all the cases. Lewis में क्या था कि वैलेंस इलेक्ट्रॉन्स ड्रॉ करके देन वी यूज्ड टू डिसाइड ऑन टू द स्ट्रक्चर. वेस्पर थ्योरी में आप देखते थे कितने लोन पेयर है कितने बॉन्ड पेयर है उसके अकॉर्डिंग. देन इन वीबीटी यू डिसाइड ऑन टू द हाइब्रिडाइजेशन. व्हाट विल बी द हाइब्रिडाइजेशन ऑफ कार्बन हियर? ट्रिपल बॉन्ड है तो sp. मैंने आई टोल्ड यू राइट इनिशियली कार्बन के पास ट्रिपल बॉन्ड है तो sp, सिंगल बॉन्ड है तो सिंगल बॉन्ड है तो sp3. तो मैंने ऐसे ना नहीं बोला, आई जस्ट मेड अ फेस. ऑलराइट, when you have a double bond across around carbon, then it is sp2, and whenever you have all the single bonds around your carbon, then it is sp3, and whenever you have a triple bond, it is sp. So generally when we talk about carbon monoxide, what I want to tell you is now whatever be the approach, it is all yielding the same results, but approach सब जगह पे different है. ठीक है? So now here what you have is 2, 4, 6, 8, and then the total bond order will be this. Please also compare it with CO plus and CO minus, and just state whether CO will be diamagnetic or paramagnetic. CO will be diamagnetic because all electrons are paired. ठीक है? And then for CO plus and CO minus also it, ठीक है? And then for CO plus and CO minus you can do it, and I will tell you how the diagram looks like. I'll draw it only from 2s. Sigma 2s, sigma, sorry, 2s and 2s. I am drawing the molecular orbital diagram for this. So you have 2s, 2s2, and see now your carbon I can show here, oxygen I can show here. Can you check out the difference? In homonuclear diatomic cases, your molecular orbital diagram was symmetric about the central line which was drawn. In case of heteronuclear diatomic, it will be a little non-symmetrical because your more electronegative element is lying lower in energy. तो oxygen इधर है तो उसका 2s इसके 2s से will be lying lower in energy, and then you have 2s2 sigma 2s2 sigma star 2s2, then this is your pi px and pi py, and this is your sigma 2pz and then pi star and then sigma star. So in this case you have 2 4 and then px के case में you have only 1 2 3 4 5 and 6, right? So the molecular orbital, हर बार molecular orbital diagram बनाना ज़रूरी नहीं है, but you should just know. Subjective paper में तो you can easily draw the diagram, but for objective you don't need to draw the diagram. You should just know that the atomic orbitals of the more electronegative elements are lying lower in energy, and if you have 14 electrons, then in case of 14 electrons what do you have? You have the order of filling similar to that of N2. The order of filling will be like pi sigma pi star sigma star. Okay, now do it for NO. अब मैंने बता दिया 14 इलेक्ट्रॉन से आगे जाएंगे तो इट विल बी सिमिलर टू दी O2 वाला केस एज O2. So now do it for NO and tell me whether NO will be paramagnetic, diamagnetic quickly. I am going to give you exactly 1 minute to tell me that. Tell me the final configuration. What is the physical properties of the paramagnetic and diamagnetic? Paramagnetics are the ones which are strongly affected by the magnetic field. They are attracted towards the magnetic field rather. In some of the books you will find that the diamagnetic substances are those which are repelled by the magnetic field. Rather, I would say that diamagnetic are the ones which are not at all magnetic in character, and paramagnetic are the ones which get attracted by the magnetic field when applied to it. And whenever you have unpaired electrons, please remember this is like a thing which is going to remain on till at least the end of chemistry, that you're going to do always, that whenever you have unpaired electrons, the substance is paramagnetic in nature. Whenever you have all the paired electrons, it is always diamagnetic. How can we find the bond order of a compound? Now here, if I am talking about the molecule here, NO, then in that case I can easily talk about NO. This is like a molecule only, and whenever you are talking about the molecule, it is like similar to that, or for a compound it can be related to the formal charge also. Is MOT applicable for d orbitals also? Please give an example. MOT is applicable for d orbitals, but it is not there in your course. MOT can be applied to your d orbitals because just as your p and p are interacting, your d and d are also interacting. But अभी आपने single dumbbell को understand करेगी plus plus कैसे interact करते हैं, d में it will be even more complicated. So it is better to do crystal field theory next year, that is there in your course. Okay, which is filled first, 2px or 2py? Both of them are at same energy, so you can fill whatever you like first because both of them are at equal energies. So उसको px को py का नाम दे दो या py को px का नाम दे दो, it's like absolutely the same. ठीक है. Now for NO, what is it is sigma 1 is, what are the total number of electrons? It is 15 electrons. So sigma 1 is, sigma star 1 is, then you have sigma 2s, sigma star 2s, then you have sigma 2pz, very good, pi star, pi 2px, pi star 2, sorry, pi 2py, then you have pi star 2px and pi star 2py, and then you have sigma star 2pz. So 15 means 2, 4, 6, 8, 10, 12, 14 and 1. So it will come either to x or y. किसी में भी fill करोगे कुछ गलत नहीं है, because both are degenerate at the same energy level, so you can just put it anywhere. And in this case, that is why is NO called an odd electron molecule? Now you know the answer. Why is it called an odd electron molecule? Because it has one electron in the anti-bonding molecular orbital which is unpaired. It has one unpaired electron in the anti-bonding molecular orbital. That is why NO is paramagnetic also, because unpaired electron हो गया, and because of that one unpaired electron in the anti-bonding molecular orbital, it's called an odd electron molecule. You can find out the bond order for this. The bond order for this would be half of, let's look into this, 6 minus 1, right? 1s has 2 and 2, sigma 2s and sigma 2s have 2 and 2. So you can just look into the pi last p orbital. So 2, 4, 6 in the bonding and 1 in the anti-bonding. So that is equal to, so that is 5 by 2. That is equal to 2.5. So the bond order of NO is 2.5. Then what about the bond order of, please compare it with NO plus and NO minus, and NO minus, and we'll compare the bond energies and the bond lengths after that. NO plus means that the electron will be given away from the anti-bonding molecular orbital. Anti-bonding orbital से गया तो मतलब ये 1 गया, so that means it is 3. NO minus means anti-bonding में आया, so that means it will be 2. So your NO lies in between this. So the bond energy trend will be NO plus will be the most stable, followed by NO, followed by NO minus. Bond length trend will be trend just the reverse. So please be very careful with it and you will be able to do it. Actually, when you actually draw for the NO, you have how many electrons? Valence electrons 5, and you have for oxygen is like 6. Okay, and it needs only 2 from nitrogen, but nitrogen needs 3 more. Nitrogen needs 3 more, so what it does is it puts here 3, and this is like some kind 2 to पूरे बन रहे हैं, ठीक है, and the third one is like not there. So basically it's just drawn as a combination, like it needs 3, nitrogen needs 3, but it needs only 2. So that is why it's an odd electron molecule, because of this one lone pair and you have 2 bond pairs, and then this one is also coming in the shared form from the oxygen itself. So it is like, so half, because the contribution is only half. So in this case you have the bond order as 2.5. So that is what you have to understand now. अब आपने सब कुछ कर लिया. You've done VSEPR. That was like the most simple one. She was asking how do you represent a bond order of 2.5. I stated that you've already now done VSEPR, जिसमें आप वो Lewis structures वगैरह draw करके you find out the number of bond pairs and the number of lone pairs. Then you have done now valence bond theory, according to which you can find out the shape, geometry and the number of lone pairs also from the excited state configuration. And now you have done the molecular orbital theory, which directly gives you the bond order. तो आपको जो भी method follow करना हो, this is the easiest, I believe, for the molecular orbital. How to now represent? I stated that nitrogen has how many valence electrons? 5. So it has 1, 2, 3, 4 and 5. It needs 3 more from oxygen. Oxygen has 1, 2, 3, 4. I will just take it like that. 4, 5 and 6. ऐसे देख लेते हैं, ठीक है. Nitrogen, oxygen needs only 2. So it has taken up these 2. Nitrogen needs 3. So it will take up 3 like this. Alright, the bond will be formed between this and this. So 2 bonds are pura and 1 bond is half. क्योंकि पूरा इलेक्ट्रॉन तो नाइट्रोजन से आया ही नहीं ना. So that way, and that is why it takes up one extra additional of oxygen to show it like this, but this is not 3. Why is this not 3? Because only 1 electron is there in oxygen, which does not have another one to pair up with in nitrogen. Okay, now with this the molecular orbital theory is like complete. I mean, you can take up any other example that is given to you, and all you need to do is like remember that you can easily find out the bond order. Greater the bond order, greater will be the bond energy. Here greater bond energy means it is the energy required to break that bond. कितना stable है, जितना ज़्यादा bond energy means bond का energy, जितना ज़्यादा bond energy होगा उतना greater will be the stability. Then after that, after talking about the stability, bond length will be the reverse order, because this is what we had done even in the last class, that bond order is directly proportional to bond energy, is inversely proportional to bond length. So this is something that you have to remember. And remember that whenever you have all paired electrons, it will be diamagnetic, and whenever you have unpaired electrons, it will be paramagnetic. And then whenever an electron is removed, anti-bonding is always more destabilizing and bonding is always more stabilizing. Bonding orbital, molecular orbital का energy will always be lower than the two combining atomic orbitals, always. बराबर पे भी नहीं होगा. The bonding molecular orbital will always lie lower in energy than the two combining orbitals, and the anti-bonding molecular orbital will always be lying higher in energy than the two combining molecular atomic or two combining atomic orbitals. Okay, and then whenever an electron is removed from the anti-bonding means more stability. Whenever an electron is added to the anti-bonding, it means less stability. Whenever an electron is removed now from bonding molecular orbital means less stability. Whenever an electron is added to the bonding means more stability. This is clear from the bond order formula, that is half of number of bonding electrons minus number of anti-bonding electrons. Whenever an electron is added to the anti-bonding means less stability. कम हो जाएगा bond order. Whenever an electron is removed means more stability. Whenever an electron is added to the bonding orbital means बढ़ जाएगा, तो more stability. Whenever an electron is removed from the bonding molecular orbital means less stability. You can relate it to the formula directly. समझ में आया? This is put in statements many a times. So now let us take up some examples and questions now. Before taking up the questions, there was a doubt of H2SO4. How do we represent the H2SO4? I will represent the H2SO4 right here, right now onto the board, because this is something that we done in Lewis structures. एक क्वेश्चन था ना H2SO4 का, draw the structure of H2SO4. So the structure of H2SO4 will be H will be combining only with O to form that. You have your sulfur as the central atom, so you have SO, means it's surrounded by, O is surrounded by what? O is surrounded, the central atoms S is surrounded by 4O, H2SO4. The chances are hydrogen goes with the more electronegative atom. So H will be going with O only, and then you have O and H, and you have a double bond and a double bond here. So this will be the structure of H2SO4. Somebody had put this question. So you can arrange your electrons and find out that H2SO4 is something like this. And even when you actually, you can try out the hybridization also by the normal method for sulfur here. Sulfur ka oxidation state will be, what will be the oxidation state? This is another question that is asked many times. X minus 8. O is 2 minus. So X minus 8 plus 2 is 0. So X is equal to plus 6. So plus 6 के लिए मतलब in the excited state you should have 6 single electrons, and you can just draw it accordingly, and you will find that there are 2 electrons, lone electrons left in the end. If you correctly remember hybridization, 2 electrons will be left in the end. That will result in the pi bond formation. So you can get the structure. What is the limit of the bond order? See, the bond order has no limits. You can find out a molecule which is randomly very, very big, and then you can actually, because it's an infinite world. But for the bond order to be equal to 0, it's like unstable completely, and so you cannot talk of any bond order which is lower than that. Alright, but and also depending upon the valence electrons now, that you have the valence electrons, then also that also decides the bond order. So the maximum of all the bond order that we've seen is maximum is 3. But keep your eyes and mind open for any kind of a new thing that can get developed. What is the limit of the bond order is done? Please explain why NO is an odd electron molecule again. See, the configuration of NO that we had put on the board was sigma 1 is 2, sigma star 1 is 2, sigma 1 is 2s2, sigma star 2s2. So 8 electrons taken care of. How many are left now? 7 more. This is for NO. So now for the 7 you have the 2p orbitals which will get filled up. So you had the sigma getting filled first for NO. So sigma 2p z2, pi 2p x2, pi 2p y2, and pi star 2p x1. So now here you have only a single electron which is left unpaired in the anti-bonding molecular orbital, which makes it an odd electron molecule and paramagnetic in nature also. Odd electron. Okay, so now before once this H2SO4 is also taken care of, now we have two more things that were included today but we had done before. One was the topic of resonance, and this, fortunately or unfortunately, somebody had asked the doubt of carbonate, if you remember, in the very first class. So we had taken it up then and there itself. What is your resonance? It is like combination, it is like something which defines, it gives you some kind of canonical form of structures which are similar, and none of the structures is actually true. You have a combined structure. Like for example, we had talked about the carbonate. Carbonate was like, you have CO2 minus tha na? So you had minus and a minus. This was your carbonate. CO3 2 minus. This is your carbonate. And in this case, I always told you that an electron, pair of electrons always get shifted towards a bond. So your pair of electrons get shifted towards a bond. Then carbon has a valency of 4. अगर ये बॉन्ड बनाएगा तो एक और दो, एक एक्स्ट्रा बन गया 2, 3, 4, 5. कार्बन का वैलेंसी कैन नॉट बी ग्रेटर देन 4. सो व्हाट विल हैव टू हैपन, वन बॉन्ड विल हैव टू गेट शिफ्टेड. अब ये बॉन्ड शिफ्ट होगा तो टूट जाएगा. सो ओनली अ पाई बॉन्ड कैन गेट इजीली शिफ्टेड. So what you have is this bond will get shifted here, and then you get a resultant structure which goes like double bond O, O minus and O minus. And similarly you can draw another structures also, such that we showed that the resultant structure is something where you have the negative charge being delocalized in between all these three bonds that we have. Because negative charge क्या हो रहा है? This negative charge is getting shifted in between the three bonds that we have. Okay, so in that case you have the resonating structure always to be in between the actual structures. It is some kind of a canonical structure which is like formed. It's not given here. Alright, not given. Then we had taken up the example of another case. You can talk about, say there was a paper which talks about, can you draw the resonating structure of carbon dioxide? What is carbon dioxide ideally? It is this. Alright, how can you actually show the resonating structure of carbon dioxide? You can shift here, and then you can also shift this bond to this place. Alright, so then in that case what will happen is, you can have O, C, triple bond O, this will carry a minus charge now, and this will carry a plus charge, because the intermediate will be O, C, C is giving and O is taking. Alright, अगर मैं सिर्फ ये डबल बॉन्ड शिफ्ट करते हैं तो this C is giving the bond and this O is taking the bond. So it becomes O minus and this becomes C plus. ठीक है, and this is like double bond. So in that case you can now say shift this bond like here. So then in that case, so from one place it is given, now it is taking, so it becomes O positive, C triple bond, O and minus. So depending upon how you are shifting the bonds, you can always put plus and minus charge and show the resonant stabilized structures. आपको सिर्फ इतना याद रखना है कि जैसे आप शो कर रहे हो, जैसे फॉर एग्जाम्पल इफ यू हैव द कार्बन मोनोऑक्साइड मॉलिक्यूल लाइक दिस, ठीक है, इस केस में अगर आप टोटल बॉन्ड को शिफ्ट कर रहे हो टुवर्ड्स ऑक्सीजन, then in that case what does it become? It becomes C positive, O negative. Just understand that whenever a total bond is getting shifted, it is like a pair of electrons which are taken up by oxygen, so it becomes minus, and the one that is giving the electrons is like plus, it attains a positive charge. Then we had seen the resonating, the most important one that you will keep doing even in your organic chemistry is the resonance stabilized structure of benzene. We have done benzene again, so let's look into something different. I am not repeating benzene again because I told you in case of benzene, one thing that I told you was that you have CH in all these points such that your benzene is C6H6. So here in this case, I told you that remember that bond will move towards the atom and from the atom the charge will move towards bond to form a bond. So this is something that we had seen. If you understood that thing correctly, you can easily draw the resonance stabilized structure of chlorobenzene. Chlorobenzene में chlorine has 3 lone pair of electrons available. Okay, so let me just draw it like that. ठीक है, look up onto the board. It's very simple. Benzene आप लोगों ने किया हुआ है सबने, so chlorobenzene should not be a difficult task to understand. In this case, the pair of electrons will move to form a bond. ठीक है, अब इस कार्बन की वैलेंसी कितनी हो गई? 1 2 3 4 and एक what you have is and 5. This carbon which is here, इसकी वैलेंसी अभी कितनी है? 1 2 3 4. But when this pair of electrons will shift to form a bond, तो कितनी हो जाएगी? 1 2 3 4 5, which is like not possible. तो एक बॉन्ड को शिफ्ट कराना पड़ेगा. किसको कराओगे? डबल बॉन्ड को. So, or I mean to have a more clear picture, the double bond will get shifted towards the atom. ठीक है, तो इस केस में अब नेक्स्ट क्या हो जाएगा? This will be Cl. Now Cl will get a पॉजिटिव चार्ज. 2 लोन पेयर्स तो वो तो रहेंगे ही, बट Cl ने एक इलेक्ट्रॉन पेयर डोनेट करा है, तो इट विल गेन अ पॉजिटिव चार्ज. दिस कार्बन विल गेट अ नेगेटिव चार्ज फ्रॉम हियर, बट साइमल्टेनियसली यहाँ से ये दे रहा है तो पॉजिटिव चार्ज, एंड दिस कार्बन एटम इज ओनली टेकिंग, सो दिस विल बी नेगेटिव. द रेस्ट ऑफ द 2 डबल बॉन्ड्स वर अनटच्ड. ठीक है, अब इस केस में this negative charge shifts towards the bond and the bond shifts towards the atom again. वही सेम, यहाँ से इस कार्बन के पास अभी 1 2 3 और एक H है. H तो है ही है. So what you have is 1 2 3 and 4 bonds हैं. जब ये डबल बॉन्ड बनाएगा तो it needs to shift one further on to keep the valency as 4 intact. So then in that case the resultant will now be, इस Cl पॉजिटिव को हमने नहीं छेड़ा, इसको भी we did not touch it at all. So now this negative has now given to form a bond. तो ये हो गया पॉजिटिव न्यूट्रल, इसने अब दे दिया तो ये न्यूट्रल हो गया. देन इस केस में इसने यहाँ से बॉन्ड लिया और यहाँ से बॉन्ड दे दिया, तो ये वाला कार्बन न्यूट्रल और ये वाले कार्बन पे, because the bond moves towards the atom. अब now this will move towards a bond and the bond towards this atom. So in this case the resultant structure will be, we did not touch this, we did not touch this, so Cl positive, this will be negative and this will be a double bond. ठीक है, and now this charge towards the bond, so this negative charge will move towards this bond and this double bond will move back to chlorine. So in this case now you get it has gone back to chlorine. यहाँ पे bond बन गया. Cl was positive, तो उसने when it took back the bond again it became negative, and positive negative neutral, so it became that. Now see, there is an alternation of bonds here. Earlier the bonds were here, now the bonds are in the alternate positions. So these are all the resonance stabilized structures. Please remember that none of these structures is a true structure. All these structures are hypothetical, intermediate, canonical form of canonical structures. These are named as canonical structures only, which are not the true structure of the molecule. It is not the true representation. The true representation comes in by a consolidated picture, which is something like this. Why is now this circle drawn? Because your negative charge is delocalized over the entire molecule. ठीक है, और फिर एक ऑर्गेनिक में पढ़ोगे एंड देन यू कैन रिमेंबर मी एट दैट टाइम. हियर इन दिस केस अगर आप देखोगे रेजोनेंस करते टाइम नेगेटिव चार्ज कहाँ कहाँ पे है, इधर और पैरा पोजिशन पे. यू रिमेंबर दिस वाज ऑर्थो, दिस वाज मेटा एंड दिस वाज पैरा. तो जब नेगेटिव चार्ज किस किस पोजिशन पे है, ऑर्थो पे आ रहा है और सिर्फ पैरा पे आ रहा है, और ये भी कौन सी पोजीशन है, ऑर्थो, तो इट इज कमिंग ओनली एट ऑर्थो एंड पैरा। तो जब भी कोई मेरा प्लस चार्ज वाला स्पीशीज होगा, जैसे NO2 प्लस, OH प्लस, ऐसे कोई स्पीशीज होगा, तो इट विल ओनली कम एट ऑर्थो और इट विल गेट कम अटैच्ड टू पैरा. So it will not occupy the meta seat, it will occupy only the ortho seat or the para seat. It will be generally positive charges, generally those are called electrophiles that you will do in organic. If it is positive, it can only come at ortho and para positions. Positive अगर charged होगा तो positive किसके पास आएगा, negative के पास. मान लो अगर मेरे पास एक, मैं इसके अंदर NO2 प्लस ऐड करना चाहती हूँ, तो वो NO2 प्लस कहाँ जाएगा, या तो ऑर्थो पे जाएगा या फिर पैरा पे जाएगा. दैट इज लाइक योर ऑर्गेनिक केमिस्ट्री दैट यू विल डू, बट इट्स ऑल रिलेटेड टू योर रेजोनेंस स्टेबलाइज्ड स्ट्रक्चर्स. So done with the resonance. Please remember that you can draw the resonance stabilized structures for any molecule. See if I am talking about HC triple bond CH, ठीक है, इस केस में हम कहेंगे रेजोनेंस स्टेबलाइजेशन नहीं है. Why? Because हद से हद क्या होगा, एक बॉन्ड शिफ्ट कराओगे, so what will you get, HC, look here, it will get positive double bond C negative H minus. या फिर इसको इस अगर इधर करने के instead of doing it on that side, you can do it on this side also. So then in that case it will be C plus CH minus, ठीक है. So that's like one and the same thing only. So you are not getting any kind of a hybrid. Hybrid is like a combination of different types. यहाँ पे negative charge was here, the negative charge was here, and then negative charge was here. It was like a complete delocalization. यहाँ पे there is hardly any scope. So we do not call them resonance stabilized. But given an opportunity or a question where you are asked to draw the resonance stabilized structure of any molecule, you know how to shift the bonds now, right? Remember that the bond can be shifted towards an atom. Whichever atom is taking it up will get a negative sign, और जिस bond से वो जा रहा है that will give it a positive sign. Clear? So resonance is like a phenomena which leads to the stabilization of the structure due to the formation of several canonical structures which are similar in energies, and none of those structures is highly stable to stay on like that. इनमें से कोई भी structure as it is नहीं खड़ा रहेगा. It will keep on delocalizing. The delocalization will be on throughout, and you know the meaning of localization and delocalization also now. Okay, then another topic that was lined up for us today was also covered up before. I'll just quickly help you remember that again, and that was your hydrogen bonding. I told you that in case of hydrogen we have done different types of bonds. We've done ionic bonds, covalent bond, metallic bonds, right? In case of hydrogen bonds, it is always an electropositive element, that is hydrogen, interacting with a electronegative element. So hydrogen bonding is operative wherever your hydrogen is interacting with an electronegative element. The only thing is you talk about it differently because the values are very, very different. Say for example, if you have to talk about COOH and you talk about say NO2, alright, or you talk about NO2, then in that case just look up here, or I can talk about even then in that case what kind of bonding will happen, intermolecular or intramolecular? Be confident about it. If it is happening within the same molecule, you call it intra. If it is between two different molecules, then it is inter of the same type. So in this case it will be intra. Generally याद रखना, whenever you have some ortho placed substituents, please look for intramolecular hydrogen bonding first. You tell me whether there is any intramolecular hydrogen bonding possible in these two. Is there any intramolecular hydrogen bonding possible in this particular molecule? No, because we do not have any hydrogen here, right? So in this case, there is like no possibility at all. But if I have Cl and OH, now there is a possibility of intramolecular hydrogen bonding. So just look carefully into the molecule. And I have told you, whenever we talk of the melting point, we lay more emphasis on the intramolecular bonding. And whenever we talk about the boiling point trends, we lay emphasis on the intermolecular trends, intermolecular bonding. Like for example, I had taken up an example and I will quickly take it up again. For this orthodichloro, metadichloro, and we talk about paradichloro. In this case, the highest melting point will be that of para. The highest melting point will be that of para. Why? Because it fits in the best into the crystal lattice. Crystal lattice मतलब it's like a solid state structure, cubic type का, जिसके अंदर you will have positionings. So because जितना ज़्यादा symmetrical उतना ज़्यादा उसका melting point. Because crystal lattice उतना ही ज़्यादा symmetrical होगा. But when we talk about this orthodichlorobenzene, in this case there will be highest boiling point in this case, because in orthodichlorobenzene ये सारी जगह पे H है, जो नहीं शो कर रखे वहाँ पे क्या है, हाइड्रोजन एटम्स. सो इन दिस केस दिस हाइड्रोजन एटम विल बाइंड विद दिस हाइड्रोजन एटम विल बाइंड विद दिस. सो द बॉइलिंग पॉइंट विल बी द हाईएस्ट फॉर orthodichlorobenzene because of intermolecular hydrogen bonding. Okay. Now let's take up some questions. If attraction is between the ion and opposite pole of any dipole, then also you get hydrogen bonds. Okay, now quickly let's take up some questions. You are given, say, on the base, let's take up the MOT questions first. On the basis of MOT, the formation of which is not possible. Just tell me, H2, H2 plus, He2 plus or He2? He. On the basis of MOT, sorry, which of the formation is not possible? H2, H2 plus, He2 plus or He2? He2. So the last option is the correct one. Why? Because the bond order will be 0. Whenever the bond order is 0, you do not talk about its formation at all. Please tell me the bond order of He2 plus quickly. Thank you. Tell me the bond order of He2 plus quickly. So it will be half. Number of bonding electrons will remain as 2. He2 plus means one of them has been removed from the anti-bonding molecular orbitals. That means 1. So that means He2 plus has a bond order of 0.5. So He2 plus is still more stable than He2. ठीक है, ये सब चीजें तो अपने आप अब पता होनी चाहिए. Which of the following has maximum dipole moment? Now NH3, NF3, this is a revision from last time, NCl3 or Ni3. Which of them will have the highest dipole moment? NH3. Why not this and this? Because they are again also electronegative in nature. NF3 का याद दिलाती हूँ. In case of NH3, what we had was, we had a lone pair and you had H. So all of them were facing in the same direction. So the net dipole moment was all going in one direction. Whereas in case of the moment in all the rest, let that be X. In all of the rest of the cases, your F, Cl and I all are electronegative in nature, and the electronegative will face opposite now to the direction of the lone pair. So then in that case they just cancel out the effect, and the net may be, maybe in the downward direction or upward depending upon the magnitude, and therefore this will be lesser than that of NH3. Which of the following combination is most likely to form predominantly covalent compounds? ठीक है, Question is, which of the following has is most likely to form predominantly covalent compounds? The options are Na and H, Br and F, Mg and O, Cs and F. Which of the following has majority chances of forming a covalent compound? Quickly tell me. Very good. It will be Br and F. They will have maximum chances of forming a covalent compound, because what is a covalent compound formed between, if you remember, electronegative and an electronegative element? Somebody said something wrong. Whenever we talk of ionic bond is electropositive and electronegative. Whenever we talk of covalent bond, it is electronegative within electronegative. Whenever we talk of metallic bond, it is electropositive and electropositive. And whenever we talk of hydrogen bond, it is hydrogen atom and an electron negative. Okay? Now another question, which is the correct about bond order? I will read it out for you and listen carefully and tell me. A, B, C, D will be the options. Which is the correct about bond order? Smaller the bond order, larger the bond strength. Smaller the bond order, this is second. Stronger the bond. Larger the bond order, stronger the bond. Larger the bond order, larger the bond length. C. If you were hearing me carefully, third option, that is larger the bond order, larger is the strength. Okay. Then pi bond is formed by the overlapping of orbitals A along the axis, B in a plane on adjacent atoms, C in a plane not on adjacent atoms, and D in a plane of different atoms. I repeat, pi bonds, nahi, option hai, pi bond is formed by the overlapping of orbitals. Along the axis? No. In a plane on adjacent atoms? Yes. Adjacent atoms pe to hote hain pi bonds, and then it is like in a plane. At least they are in the same plane. So pi bonds are formed by the orbitals on the adjacent atoms but the same plane. Now according to Westport theory, which is the correct with respect to repulsions? They are comparing lone pair, bond pair and lone pair, bond pair. So you tell me, lone pair is greater than bond pair is greater than bond. Okay, consider the solids CO2, CO2, NaCl, diamond and metal. Which of the following is correct about the bonding of these solids? I repeat, A is CO2, okay? Just think about the bonding. A is CO2, B is NaCl, C is diamond and D is metal. Now you have to tell me, A is which one of them? I've told you, A is carbon dioxide, B is NaCl, then you have diamond and you have metal. Alright? You have to tell which of them is covalent, van der Waals forces, which has van der Waals, which of them is ionic and which of them is metallic. This was a question, and this was like a question of IP in fact, so it was like not that very difficult. The number of unpaired electrons in O2 minus, and you have 4 options. You want the options? Should not need. The number of unpaired electrons in O2 minus. O2 minus means I am talking about O2 molecule ka minus. The number of unpaired electrons in O2 minus. Very good. It will be 1. All of you all, please be thorough with these molecules for your entrance examinations. The molecules which are asked are N2. So N2 के सारे species, N2 plus, N2 minus, N2, I mean just think about that. Then O2 के सारे species, O2 plus, O2 minus, O2 2 minus and O2 2 plus. Alright, please be very thorough with these two, and then these are by and large the most important ones that you need to नो thoroughly. So if you are well prepared, एक दो बार इसको अच्छे से कर लोगे तो you will remember the answers automatically also. Alright, and then apart from these four, you should also know that which are like not possible. Ne2, He2 and so on. For any of the noble gases, whenever you actually duplicate them by in forming a homonuclear diatomic cases, in all these cases the bond order will be 0 and hence there is no possibility of forming the bond. Okay, so now the formation of molecule which is a square planar one requires hybridization of square planar. Here I would like to tell you that this is something that you have not done. You have done sp, sp2, sp3, sp3d, sp3d2. There is another configuration, the hybridization which is possible, and that is dsp2. d2sp3 is also like possible, but presently I am talking about only of dsp2. Let me tell you, this is like generally possible for the d block elements which are not there in your course right now. D block elements are the transition elements in which your d orbital is getting filled up. So any kind of shifting of electrons will happen from the d orbitals. अभी तक आप p को d में shift कर रहे थे, ठीक है? So any kind of shifting will happen from the d orbitals. So in this case, dsp2 happens in case of NiCl4 or something like that. So here dsp2, I can only tell you that this possesses a geometry which is square planar. So please remember this as of now, dsp2, because it's altogether a different way of doing hybridization in case of complex compounds. It is a little complicated to understand right now. I do not want to confuse your basics. So dsp2, here dsp2 has is possible only for complex compounds and it has a geometry of square planar. So please remember that if I am asking you a question, the formation of a molecule which is square planar requires the hybridization of dxy s px py. No, because this is ds. This is like, oh, the only another thing is that in dsp2 the d orbital which is involved is dx square minus y square. Alright, please remember that. For dsp2, the orbital which is involved is dx square minus y square. Otherwise, you can have dxy, dyz, dzx also, and what is the fourth one? dz square. So the d orbital which is involved in the dsp2 hybridization is dx square minus y square, and what is the geometry of this? Square planar. This is only for you to remember as of now. I am not explaining anything related to it. The hybridization can be used to account the shape of ClF3. What is the hybridization of ClF3? We want the hybridization of ClF3. You should not take so much time. We want the hybridization. You have 7 valence electrons, 3 being used up, so 2 lone pairs, 3 bond pairs, so a total of 5. There are many ways of doing it. अब तो आपको सारे ways पता हैं, ठीक है? अगर Vesper से करोगे, so what you have is VSEPR theory से you have 7 valence electrons, 7 में से 3 ने तो bond pairs बना दिए, ठीक है? तो 3 bond pairs, बचे कितने? 4 electrons means 2 lone pairs, so total is like 5, and 5 means sp3d, 1, 4 and 5. So it is sp3d. See, in this particular question set that I have, they have put it as dsp3, dsp2, sp3 and sp2. So in that case, the best option suited from out of these 4 is dsp3. Ideally, this is not the correct way of writing, but the option will be then dsp3. Clear? There is a difference. Okay? Now polarization. All of you understand what is polarization? Whenever your cation is able to polarize the anion and it is introducing covalent character to it. What rules are these? Fajan's rule. Now in Fajan's rule, what should be the size of the cation for more polarization? What should be the large size of the anion? And if your d orbitals are getting filled up, then that will also be able to polarize it more. So your d block elements which are getting filled. So anyone, that was like the pseudo noble gas configuration point. Okay, then which of the following has the longest bonds? This type of questions are very common. Which of the following will have the longest bond? You have O2 plus, O2, O2 minus and O2 2 minus. Which of them will have the longest bond? O2 2 minus, because in O2 2 minus your 2 electrons are getting added up to the anti-bonding. It will have the lowest bond order, so the highest bond length. Okay. Now the bond angles, because now all your applications, if you've understood the basics, all your applications will now come set in. So practice as many questions as you can. You have to give the bond order, the trend for bond angles in case of water, ammonia, and 4 options are of course given, methane and carbon dioxide. You have to give the bond order trend. Bond angle, I'm sorry. The bond angle trend. This you know. CO2 तो linear है, तो सबसे ज़्यादा तो उसी का ही होगा. So this will be the highest, whatsoever be the case. This is tetrahedral, this is tetrahedral, this is tetrahedral. So this will be the same. This is 109 degree 28 minutes. This is around 107. This is around 104. 104.5 degrees. ठीक है, 107. Now if I add on H2S to this, where will you place H2S? If you add H2S, सबसे पहले सोचो, sulfur belongs to which group? It belongs to the group of oxygen. So naturally it will be somewhere around this, because 2 lone pair इसके पास भी होंगे. Same case, अगर एक ही group वाला ditto same की बात कर रहे हो, so here you have 2 lone pairs and 2 bond pairs. So this will also have 2 lone pairs and 2 bond pairs. So then in that case, अब इसका angle कैसे guess करें? 104.5 तो नहीं होता. So in this case, what generally happens is, because the size of sulfur is very large, so in that case, the lone pair also is occupying a lot of space. So more repulsion, so the bond angle will get compressed even further. So in this case, the bond angle will be somewhere in 90s. Somewhere in 90s degrees. So it will be lesser than that of H2O. So remember, as the size also increases, your bond angle gets affected accordingly depending upon the lone pair and the bond pair availability. I am saying this was a normal trend that was given. ये normal examples हैं जो आप लेते हो. Just in case if you have to compare your H2O with H2S. If you have to compare your H2O with H2S. So in this case everything is just the same, because this belongs to the same group. Oxygen has 2 lone pairs, and this also, sulfur will also have 2 lone pairs. It is also sp3, it is also sp3 hybridized, but the bond angle in this case will be lower than that of H2O, simply because sulfur is larger in size. ऊपर से नीचे जाते हैं, oxygen, sulfur, selenium, tellurium and polonium is what you have. So on going from oxygen to sulfur, your size increases. As the size increases, then in that case the lone pairs will be occupying more space, because they are the orbital lone pairs. So because of that, more repulsions in the lone pair, or bond pairs बेचारे क्या होंगे? They will get more compressed. So the bond angle will be lower than that of H2O. The fact that CO2 has no dipole moment, you have to tell the reason for that. So it's all an understanding. Now first one, it is covalently bonded. That's true, but not the reason. It is ionically bonded, not at all the reason. It's angular, CO2 is not angular, it's linear and symmetrical. Symmetrical word should be there whenever you are talking about the dipole moment to be equal to 0. Okay, then which of the following statement for, this is what we've already done. Then HH bond is, this you are given. You are given the bond length of HH and you are given the bond length of Cl and Cl. Something of this sort, we had done a question last time where we had solved for Y and X type of a bond length, if you remember. The HH bond length is 0.74 angstrom. The Cl-Cl bond length is 1.98. What is the bond length of HCl? This is what we had done. We had done a similar question last time. तो इस पे ऐसे न्यूमेरिकल्स आते हैं which are very simple. That was a question I think for C triple bond N, right? When you were given the bond energy for N triple bond N and C triple bond C. यही था question last time का. Last week we had taken up a question in terms of X and Y, and what did we see? That R by 2 of N2 plus R by 2 of C2 was equal to R of Cn. Half of N2 plus half of C2 was giving us the radius of Cn. So in this case also it will be half of H2 plus half of Cl2 will be giving you the radius of HCl. Please calculate it quickly and tell me. It shouldn't be taking time. Half of H2 plus half of Cl2 should be giving you the bond. So next question. .36 is the answer. All of you all will be getting that. It's a very simple question. Nothing is to be done. Please remember, in such cases, सिर्फ R by 2 of homonuclear diatomics को करो to get the radius of the heteronuclear diatomic molecule. ठीक है? Any doubts to anyone for this? It was a simple question. Then I think we can just take up some questions which are there on the slide so that you do these ones as the homework. Now here, let's look up onto the board. What is the hybridization of oxygen atom in water? sp3. ये तो अब सोचने की ज़रूरत नहीं है, अदरवाइज करना पड़ता. इसीलिए मैं बोल रही हूँ जो स्टैंडर्ड एग्जाम्पल्स हैं प्लीज रिवाइज देम एटलीस्ट 2 to 3 टाइम्स सो दैट यू नो इट. और उसके अलावा क्वेश्चंस नहीं आएंगे, बाकी सब आर बेस्ड ऑन योर अंडरस्टैंडिंग ऑफ द क्लास. When a double bond is formed between two atoms, one of the bonds is a sigma bond and the other is a pi bond. Yeah, you all know. The pi bond is created by the overlap of sp2 is it sp2 hybrid orbitals? sp3, it is simply p orbitals. Your pi bond is formed by px plus px or py plus py, where z is considered to be your internuclear axis. Okay, now next, the central atom in Br5 has dash bonding pairs of electrons and dash non-bonding pair of electrons. Br5 means Br पे कितने 7 valence electrons, उसमें से 5 bond pair बन गए, तो clearly 5 bonding pairs, बचे कितने 2 electrons, that is 1 pair, so that will be 5 and 1, so C option. Clear? So this topic will have questions which can be done at a superjet speed also. Which of the following molecules does not have a net dipole moment? Now just think about it. Water is a bench structure, so you have O and H in H और lone pair भी ऊपर. So इधर oxygen का it will have. Then NH3 again similar tetrahedral with a lone pair. तो NH3 तो आपको पता ही है वो high होता है. BF3 is, what is the hybridization of BF3? It is sp2. sp2 means it's a trigonal planar. So that means B अगर इधर है तो one F is here, the other F is here, the other F is here. It's a trigonal planar structure and it is highly symmetrical. So each of the bond dipoles will be cancelling each other. It's a symmetrical structure, so it will be 0. Does not have a net dipole moment. Don't even look into the next then. What is the bond of NO2 plus? Now here, when you talk about the NO2 plus, you will have to look into the number of electrons which are there. So I suggest for this case you can actually draw the Lewis structure and find it out if you can. For NO2 it will be the maximum number of bonds that N is forming with O. What is the maximum number of bonds that N can form with a single O? In this case it will be 2. So the bond order, you know that the bond order is equal to the number of bonds. So in this case what will be the answer? It will be 2. दोनों तरफ को नहीं देखना, you will be checking up the maximum on one side. So 2. Okay, which is the electron pair geometry of the central oxygen atom of ozone? Ozone is kind of a linear structure and you can easily find it out also by drawing the Lewis structures that you've done with another teacher also. So that is linear. What is the molecular geometry for ammonia? Now the geometry as per the hybridization is tetrahedral, But if at all a pyramidal shape is given, then in that case you will opt for the pyramidal structure. So the option will be D. The molecular orbital diagram for C2 2 minus, I think it's 2 minus only, would show which of the following molecular orbitals. Let me tell you, this is sigma 1 is 2, sigma star 1 is 2, sigma 2 s 2, sigma star 2 s 2, pi 2p4, sigma 2p2 and so on. So please tell me which will be the correct one. Quickly do it for C2 2 minus. Hybridization C2 may 2 minus, you have to add 2 more electrons to it. So the correct option will be B. All of you all here with me? क्योंकि C2 तक क्या होगा? C2 तक it will be pi 2p4. Now let me tell you, the majority of the students what mistake they do is, आपने देखा C2 2 minus. सबसे पहले तो C2 का hybridization करते हो, C2 का जल्दी से करते हैं and then they mark for the C2 only, which should not be done in a haste. ठीक है? C2 का will be sigma 1 is 2, it is a total of 12 electrons. So sigma 1 is 2, sigma star 1 is 2, then sigma 2 is 2, sigma star 2 is 2, then you have pi 2p4, because pi 2px and pi 2py 2 and 2, and then you have sigma 2pz 0 for C2, but now that sigma 2pz will get filled once you have 2 minus. So B option is the correct one. So it is the final outermost configuration will be pi 2p4 and sigma 2p2. Which of the following represents best the three-dimensional view of NH2? NH2N. Which one? H2N, sorry. H2N. Which represents the best one for H2N? Wherever your lone pairs are like far apart from each other, and you can even try out working for hybridization in this case. Here in this case, the best option is C. Why? Because your hydrogen atom, one is coming out of the plane, the other is going inside, and your lone pairs are also situated in a similar fashion. Okay? So it's like instead of one H, you're adding instead of one hydrogen, you're adding up a lone pair. So it is some kind of that geometry only, fixed up in the tetrahedral kind. Which of the following represents the best resonance structure for N2O? Now, which of the following represents the best structure for N2O? Remember, कुछ important features of resonance. The most stable structure in the resonance will be the one in which the negative charge will be on the electronegative atom and the positive charge will be on the electropositive atom. So, सबसे पहले तो देखो, दोनों में से इलेक्ट्रोनेगेटिव कौन सा है? ऑक्सीजन. ठीक है, और दोनों का इलेक्ट्रोपॉजिटिव कौन सा है? नाइट्रोजन एंड नाइट्रोजन. Now, and look for the strongest bond जहाँ पे बन रहा है. So wherever you have a triple bond in comparison to double bond will be more stable. So in that case you will have, wherever you have a triple bond and you have the negative charge on oxygen and a positive charge on nitrogen. Because all these structures can be possible, but which of them will be the best suited will be the one, first of all, whichever will have the smallest bond length, or you can say the highest S character, and the second point is that whichever has the electronegative carrying the negative charge and electropositive carrying the positive charge. B in this case will be the best suited. Otherwise for N2O you can draw the other structure as well. This is also a feasibility, this is also a feasibility, but the best suited one will be this. Okay? Now last question, 11th one, we leave it at that. What is the hybridization of sulfur atom in SF4? You can easily tell that sulfur has 6 valence electrons, so 4 bond pairs, 4 plus 1, so sp3d. You're saying D, so it is sp3d. So this is like something that you're very good at now. So all the best for your test, and please perform well and practice as many questions as you can. Okay, then only there is like some benefit of doing what you're doing. All the best. Thank you.